Alright, are we live? Hello? Hello? Welcome, welcome. Howdy. Howdy. Such a beautiful day out today. Finally the sun is shining. It's the middle of summer. It's fantastic. Yeah, so hello and welcome. I'd like to get into the next question here. Let's get that going. Just gonna solve some problems today. Let's do that. Maximum XOR of two numbers in an array. Also, praise God for another day, man. Praise God for another day. Happy Memorial Day, too. Given an integer array nums, return the maximum result of nums of I XOR nums of j, where 0 is less than or equal to I, less than or equal to j, less than n. Could do this in linear time, runtime. I think so. Interesting. So, if you XOR two numbers, you're going to get the largest possible number. If you don't have two numbers, then you just return 0. Or, actually, if there's only one number, that's a little confusing, but what do you get if it's just one number? This is an interesting question. This is kind of a maths question. Okay, so you get 0, but it's less than one number. All right, so that's kind of an edge case. We'll just take care of that now. Otherwise, you would take the XOR, right? You do 1, 1 should give you 0, I think. Let me just see. Yeah, okay. So this is an interesting question. Obviously, there's a quadratic time complexity where you just take every possible pair from from left to right and get the maximum. There is maybe a better way of doing this. I guess I'd have to ponder how you could do this more efficiently. There's probably some maths trick somewhere in there. So the deal with XOR, the XOR function, is all of the bits that have a difference, those will come out to be a 1 in the result. And in other words, it's a bit-by-bit comparison of the number, right? So you convert the number into bits, zeros and ones, into binary, and then the XOR you do an operation bit by bit, by sort of piece by piece. And if there are two 1, if it's a 1 and a 1, then it doesn't end up in the result, it ends up with a 0. If there's a 0 and a 0, it ends up with a 0. But all the other two cases, if there's a 1 present in only one of the numbers, or one of the numbers, sort of you have number A and number B in that particular bit slot. If there's a 1 for A but a 0 for B, then your result, we'll call it C, would be a 1. And similarly, if there's a 0 for A and a 1 for B, then you'd also have a 1 for C. So that may or may not be something we can take advantage of to do this more efficiently. Like there might be something there, like a bit-by-bit kind of manipulation where I guess basically we're looking for the pair with the largest number of disjoint bits, something like that, or yeah, we'll call it disjoint, or yeah, the smallest intersection of bits is maybe another way of expressing it. No, it's not necessarily the smallest intersection, it's the largest. It's like the opposite of the intersection, the largest number of bits that are disjoint. That's probably the way to express it. But that's not even necessarily true either, because each bit has a different amount that it's worth. So you actually would want the most significant bit the most significant bit is more significant than all the other smaller bits. So we actually don't even care about the smaller bits if we have. So actually we could go sort of bit by bit through all the numbers, I guess, to find the pair for which that first bit. So we can reduce the question to only caring about the most significant bit, and then I guess so you could do that same routine on every bit, right? Only really care about one particular bit at a time, and the first bit where that there's any pair where that bit exists, that's a better choice than all the other pairs, right? All the other possible pairs are just thrown out immediately. Although you could have a case where actually that doesn't necessarily narrow it down to one pair. It could be multiple pairs that have that for most significant bit in the result. In which case you'd want to like each time you process the bits, you would reduce the number of pairs to consider, I guess. Although that doesn't seem like the most efficient way to do it. I mean, even if it takes linear time each time, the problem is that the set of things to consider is still, well, no, actually it's a linear set. No, well, the number of pairs is a quadratic set. Excuse me, so if you were to try to store all those, because it's a quadratic set, you're stuck with quadratic runtime complexity in the best case. So actually you don't want to keep all of the possible pairs. You probably want to keep you probably want to keep some, I guess, some filter, some data structure that would like filter out. Yeah, you can maybe create like a bit mask that would eliminate your the elements, the other pairs, something like that. I'm not really sure, actually. I also don't mind me just. It's a good idea to keep your hands away from your face. I don't tend to do that. My face is kind of marred up because I don't resist touching my face. Get dirt and oil all over my face. Not obvious to me immediately how to solve this problem. Definitely an interesting one. What are the bounds on the numbers? Maybe that's relevant. Are there any integer really? Okay. You're trying to find a pair of numbers. Something kind of interesting. So you may be able to do some kind of dynamic programming solution here, possibly where you could say the optimal pair including this particular number, and then the optimal pair that includes this particular number, and then the optimal pair that includes this particular number, sort of from left to right. Or I guess there's a different way of doing it, but I think that's one approach. Like, yeah, the optimal pair including this number, considering all the other numbers, that has a certain value, right? That has a certain like pair associated with it at that point. Similarly, at 10 and comparing to all the other numbers, that also has a certain sort of index associated with it, and so on. And then you could take of all of those possibilities, you could take the maximum. That would be a correct answer, but that's not really too different from doing exactly what I described before, which was a brute force approach. That's basically the brute force approach. It's pretty much the same thing, with a naive approach. So you probably would want something a little bit different. Alternatively, you could maybe find the optimal within only considering 3 or only considering 2 numbers, right? So that's you have that kind of default by default. Like maybe there's an inductive kind of argument. Now, if you consider this next number 5, and you compare that to the other possible numbers, which one would give you the most significant bit or bits? I'm not really sure I like that one very much either. I think the idea I had before about like going bit by bit and using the most significant bit is probably the best approach, or maybe not the best approach, but maybe that's a better way of doing it. That might be where we should focus. Because you can at least partition your set into 2 pieces. You can say here are numbers that contain that bit, and here are numbers that don't. So you could pair off any 2 of those numbers together, and you'll have that most significant bit. And then you want to go to the next bit and say, okay, at that point you'd have another kind of split of different number of again, you have another partition. However, between those 2 partitions, there might be a pair between those 2 partitions, there might be a pair that can be made of both of those partitions, and then that would give you both of those bits, right? That would be better than any of the other possible pairs at that point. I kind of want to say something like that, is that if you were to partition your set based off of the numbers that have a bit and don't have a bit for each bit, so you have 32 different partitions, and then you were to find, right, and you can kind of rank them most significant to least significant partition, then you'd want to find a pair that is in as many partitions, it's present in both of those partitions, right? In other words, there's sort of one in the, I guess we call it the left and the right side of the partition. So there's an element to the left side, an element to the right side, and that same element to the left, element to the right, it could be inverted, right, where it's on the right and the left, but that pair could be found in each of those partitions. As deep as you can go, right, if there exists a pair that is present, then as deeply as you can go, that's actually going to be your answer, right? That's going to be the optimal. As deeply as you can go into sort of however many layers you can go into those partitions, right? There's only 32 of them. It's a constant number in this case. That's gonna excuse me, that's gonna be your solution, is the one that's the deepest there, right? Because that's gonna have the most number of most significant bits that are flipped to true in the result, right? So that's by definition the largest number, or yeah, it'll be the largest number. Now, the tricky thing about that is, okay, we could create each of those partitions efficiently, right? That takes linear time. That's relatively easy. However, sorting out which pair has that sort of longest chain of existing in that way in each of those partitions is maybe not the most obvious thing. I guess you would, because enumerating all of the pairs in the first partition is immediately immediately a quadratic time complexity approach. I guess what you would want to do now, because there's only 32 partitions, in theory you could walk through each number and check to see if you could process each number through each partition and eliminate a number at a time using 32 operations, then you're in good shape, right? That's fine. I guess the question would be, does this number exist well, all the partitions contain all of the numbers, right? So I guess really the issue is if we look at 3 in the first partition, the second partition, so on, it'll be, on one side or the other, either the left or the right side. And obviously there's some other number on the other side that we're interested in, but we want to see if the other side of that partition also has a number that's sort of present in those spots. It's a little confusing how to express that, but basically, like, let's say you have maybe 3, or not 3, but there's some number where you have a left, it's on the left, then it's on the next partition, it's on the right, the next partition is on the left. You're looking for a number that's kind of mirrored, where the other number would be present on the right, and then on the left, and then on the right. So it has an inverse pattern, I suppose. So that's kind of interesting. Well, that would be quadratic time if we went through every number. Which I'm thinking about, like, using kind of a bit mask or something. I want to say something like, actually, you could, I don't know. No. Assuming all these partitions, because some of the partitions could actually be empty on one side or the other, in which case you would ignore that particular bit. I'm just thinking of like a kind of almost like a bit mask, like what's the largest, how deep can you possibly go? I don't know. It's a tricky question. I didn't really think about this. Right, because if one of the partitions is just empty, then you kind of just skip that one, where one or the other, no matter what, or rather, yeah, basically the bits all set to 0, all set to 1 for all the numbers in the set. Right, that particular bit you just skip, you'd ignore, because it's just going to be the same for everybody. So, like, let's just try considering 1 bit, right? So 1 bit, we would immediately have a whole two two partitions, assuming that this partition is not empty, and then all of the pairs, it's sort of a round robin, right? Any of the things on the left side paired off with any of the things on the right side, all of those possible pairs give you a solution that'll have that most significant bit flipped to true. Now we want to consider the next partition where we say, okay, now let's say the second bit, we want that to be flipped to true, right? And again, we have, let's say it's non-empty, the partition, right, the left and the right, both are non-empty. Again, any of those pairs from the left with the right, all of those will have that second bit flipped to true. But now, how do we combine that information of the first set of pairs and the second set of pairs efficiently? We want to do that in basically in linear time, I think. Yeah, we want to do 32 times linear. So in linear time, we want to figure out which, basically, I guess, a new partition on the left side, a new partition on the right side that consists of, it's actually not necessarily left and right. It's like basically where, well, yeah, I don't know actually. I don't know how to, because some of the numbers on the left side in the first partition could be on the right side. Oh, ouch! Oops, I was supposed to do that. Keep messing with my nose. Oh, I should have done that. Ouch. That's why you don't touch your face. I have a scar on my nose now because I scratched it when I was trying to heal. That was bad. That was a mistake. Mistook my own skin trying to heal for a piece of dirt to pull off. Now it's just trying to heal, but it's, yeah, it got dirty and then developed a what do they call that? So a blemish trying to heal itself. So anyway, so yeah, the things on the left, like if you consider the first partition, the second partition, the things on the left side and the right side of each of those, things on the left side of the first partition could end up in the right side of the second partition. We're looking for any pair that exists in the first partition and similarly exists in the second partition. They could be mirrored, though, in the second partition. They're not necessarily on the same side. So what would that look like? Well, we know that every number, for every possible number, let's say starting the left side of the first partition, exists somewhere in the second partition, given that they're not empty. And similarly, the other possible pair on the other side, the other partition. Now, here's the tricky thing, right? So if you look across, so you start look at partition 1 and the left side of partition 1, grab some value, we'll call it A. Then there's any B you could grab on side 2. The issue is that B would be not something you want to consider if B is also present in the same side that A is on the second partition. There we go. Yeah. So we could throw out B as a pair to A. Now what's tricky about that is that although we've eliminated the pair to A, we didn't eliminate A as a possibility altogether, right? Because there could be a litany of other possible right, there could be a whole bunch of different values for B. So so really it would be all of the things in the first partition on the right side, let's say, if any of those are also present, I don't know. It's kind of some kind of a filter. Like, I don't really know how to express it. It's like, it's just, really breaks down to there's how many different possible pairs, right? So I don't know, man. It's hard. It's hard. We want things that'll get you 1 1. Given we have 0 0 0 0 0 1 0 0. Yeah, see see it gets interesting. Gets interesting. Right, for 0 0 and 0 1 1 0 1 1, right? The only way we get ones is are these two. But now let's say you're dealing with 0 0 oops 0 0 0 1 1 0 1 1. These 4 possibilities. And those show up 4 times for the next 1 2. It's going to seem a little confusing at first. When you copy all of these, you get the same, what do you call that? Kind of, also I probably could just type these. Probably should just type these. Nice. It's probably a lot better just to type it. Oops. What was I even saying? Where do these go all the way at the bottom? Probably did this wrong. There's probably a better way to do this. It's quicker. But of all these different possibilities, I guess what I'm trying to say is that there's a way to filter this such that I'll explain in a minute here. Trying to say is that clearly this setup partitions you could partition your elements into 2 groups, some of them that have a 1 and some of them that don't have a 1 in that particular bit, and any pair from those 2 groups will give you something where that significant bit is set. And you can do that for every bit, right? But you have something a little more complicated going on when you start to try to consider like 2 bits, right? And that's this kind of deal. Because we want 1 1, right? So all of these will give you 0 0. I probably should have just done it right next to each other. 0 1. Even though there's only 4 possibilities, there's a lot of different ways to get there, I suppose. 1 1. 0 1. 0 0. 1 1. 1 0. 1 0. 1 1. 0 0. 0 1. 1 1. 1 0. 0 1. 0 0. Okay. All right. Not the cleanest way to do this. But these ones are the ones we want, right? And that's kind of the deal. That's part of the issue is that like this one, oops, Oh, wait. Okay, that's it's like not the best. 1, 2, 3, 4. There's only 4 ways that this works, right? There are only 4 ways that this works. And everything else doesn't work. But basically, somehow we want to make that jump to having 2 bits considered now, and eliminating some pairs based off of 2 bits. That's kind of what we're getting at here. So you can actually break this down into 2 sets, or a partition. Yeah, you can actually still partition this, I guess, using 2 bits. So the partitioning would be a partition where both of the bits are set and none of the bits are set, right? And any pairs between those 2 would work. Or that's one partition that'll work for 2 bits. The other partition would be, right, that's this part, so that's sort of this one. That always works. The other partition you could use for the pairs would be pairs where the first bit is flipped on and the second bit is flipped off, and the first bit is flipped off and the second bit is flipped on. And similarly, that's actually the same partition for both of these cases. So there's sort of these 2 symmetric cases. So that's how you could consider. That would give you 2 partitions for 2 bits, and all of those pairs would give you the optimal. Again, this is assuming, well, any of those pairs will give you sort of the optimal. And that should only take linear time to create those 2 partitions. And you get a very large number of you get a set. So yeah, basically that would be 2 partitions, and any of the pairs between those 2 partitions would give you those 2 most significant bits that you're looking for. Interesting. So it's a bit mask, right? So a bit mask for the 2-bit set, and then 2 bits on, 2 bits off to partition, and then also a bit set for 1 bit on and 1 bit off, and vice versa. Any pairs from those sets will give you those most significant bits. And again, we're assuming that right, if the bit mask is I want to say it has to match that bit mask, I suppose. Like those 2 bits have to match the bit mask. I guess what you would do is you can make all zeros for all the other numbers and do an AND. And if it's 0, if it's all, the whole thing is 0, that means you don't match. Or you have to actually have to match these exactly. So how do you enforce that? How do you actually have a bit mask that matches exactly? I didn't really think about that. Pretty sure there's a way to do that, but we should probably get that first before we continue this line of reasoning. Because if you can't match it exactly, excuse me. you match it exactly? Really gotta think about this. An AND is not enough. The 2 bits matching this pattern. Which, by the way, we could produce the other bit set just by using an XOR, right? So it's 0, 0, and then XOR 1, 1, and right, those are symmetric, and then 0, 1, XOR 1, 0, those are also symmetric. XOR, not XOR, bit flip rather, bit flip the bits. Just, but we also want to filter, so all of the numbers that don't have the first 2 bits set to 1, we want to put that in one side, and all the ones that do have it set to 1, we want to put another side. We want to differentiate based on that. So oh, I know. Yeah, okay, duh. That's easy. Alright, got it. No, that's fine. You could do the bit mask, you just make everything else zeros, and you AND this, right? So you have the sort of first 2 bits set to whatever you want, everything else is set to 0. You AND that with a number that you're interested in, and then you check to see if this is equal to what you just, I guess we'll call it the, I don't know, we'll call it mask M is the 2 bits set to 1, and then all the other bits set to 0, so we'll call that M. You AND M with a particular number, we'll call it A, so M and A, bitwise and then check if that result is still equal to M, where all the 0 bits should be flipped to 0, all the ones you don't care about are set to 0, but these 2 bits that you're interested in should be exactly equal to what we said in M. Express it that way. So yeah, if you do 0, 0, then everything should be 0 across after you perform an AND. 0, 1, same thing, these 2 bits, it'll be 0 and a 1. Now the tricky thing about that is, I don't know if that's exactly correct, if that works the way we'd like it to. Because you could have both of these bits set to 1. Right? If you just have both bits set to 1, and you AND with 0, 1, then it will be 0, 1, but it doesn't necessarily mean that it's exactly, it doesn't mean that those exact bits were set to 0, 1. Yeah, it's a little confusing. That's very confusing. I think actually the way you're supposed to do it is do an XOR. So you would, I think the first, yeah, I think it's maybe 2 steps. So you would AND with a bit mask where you would throw out all the bits to the right, right? So make all the bits to the right 0. So that's using a bit mask to do that. And now you're only considering the first couple of bits, most significant bits. That shouldn't be too hard. I think you could come up with a mask to throw out the bits. And then the bit pattern you're interested in that you want to match, then use an XOR. And if it's 0, that means it matches. If it's not 0, then it doesn't match. That's the way to do it. Yeah, that's correct. Right. And so anyway, so that's right. So okay, so we could filter that way. So that's fine. But that, I mean, I don't know if this necessarily works for all the possible like sequences of bits. So for 2 bits, we have 2 partitions. That's fine. But what about 8? What's that going to look like? So that would be sort of 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 110, 111. Right, that's 1, 2, 3, 4, 5, 6, 7, 8. Right, 8 of these, and this pattern is going to show up 8 times. Right, so if you did 0, 0, 0, 0, 0, 0, 0, 0, 0, do that a few times, a couple times. Right. Same thing for 111. Oops. Okay. Oh, actually that should be further down. That's not the right spot. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Right. This is just going to get copied. This is just going to be copied over and over. Down here. Actually, this is going to be copied 8 times, this one. 0, 0, 1, copied 8 times. Some of the buttons don't really work the way I would expect them to. Yeah, so you can see this is sort of it's kind of interesting what's going on here. This is definitely a lot, very quickly, right? This goes from 4 to, it looks like 4 by 4, which is 16, to so this is like 2 by 2, 4 by 4 is 16, and this is probably 8 by 8, which is 64, right? So it's 4 times this one. So it's quite a lot more things to consider, I suppose. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And then we want a similar thing. I do this 8 more times, right? Do it 8 more times. So. Right. Actually, I could be a little faster about this, I think. Okay, so it's only half of it, or not even half. So bear with me on this. It's gonna take a little bit of time. Now, obviously, a lot of these we know are not going to be fruitful. However, in order to be certain we're doing it correctly, kind of want to go through all the cases, right? Because we haven't really explored enough to see the full pattern to really know whether or not we're in the right here, or like what to expect. All right, 0, 1, 2, 3, 4, 5, 6, and this should be 7. Okay. All right. Yeah. Realize that's quite the 64 of these to go through. So what we can do is actually just select the ones that I know will be meaningful. So clearly only this one, right? we know that. It's kind of obvious. Only this one. And only this one. If I want the ones that the result gives us all the bits filled. In fact, it's exactly the negation. In fact, it's exactly the negation. That's what we're looking for. Only the negation in each case. Yeah. That's it. Actually, I think every one of these you only get, it's only the negation. Yeah, I think that's it. Only possibility that we care about. So really it's, yeah, okay. So, okay, how many partitions do we get then? For 3 bits, we have 1, 1, 1, 0. It's paired off it with 1, 1, 1, 0. Then we have 1, 0, 0, 1 and 1, 1, 0, which again is another 0, 0, 1 somewhere around here. This one. Alright, these are the same partition, basically. 0, 1, 0, 1, 0, 1. Did we do blue? We did. Orange, red, green, to green. So there's 4 partitions now. 0, 1, 1, and 1, 0, 0. Okay, so this isn't too bad, I guess. Basically, the number of bits that you're dealing with, you would have 2 raised to the b, we'll call it, numbers to consider, and then 2 raised to the b minus 1 is the number of partitions to consider. And the reason for that is because the other part of the partition is just going to be sort of the bit mask of the inverted bits, right? The negated bits. That's why you divide by 2. It's because all of these are sort of symmetric across. And that's the other thing too, is that the only pair that works is exactly the negated bits. So there is really only one pair. So it's actually just every for all the bits, it's just every number, it's a negated pair, and then because there's symmetry, you don't actually need to go through all the way through. You only need to go through half of the numbers, and then you would have already considered the other I guess the other part, if that makes sense. So, the other part, you'd have already considered the other part. So 0, 1, 2, 3 is as far as you need to go, and then now you're already looking at the same thing in 3, 2, 1, 0. Yeah, so that's interesting. That gives you 4, right? That's the number of partitions. You have 4. 0, 1, 2, 3. 0, 1, 2, 3 is 4 numbers, right? Which is 2 to the 3rd divided by 2, right? Which is, 4, right? Okay. That's an exponential number of partitions to consider, though. And basically, any element from any of those, any 2 numbers from any of those sets. So any of those partitions, any 2 numbers from those would be a possibility. Would be an optimal number. Would give you the largest possible number. actually what we're looking for is, since B is 32, 2 to the 31st different partitions. That's a lot. That's a lot. Possible partitions. That is many. So I guess, huh. I think you can do this relatively efficiently then by determining, I guess, because really you could take each of these bit masks and kind of you can go sort of the other direction, where you could say, you could start with a result of 111 and then say, are there any if you took all the numbers and filtered out to only these 3 bits, to consider only these 3 bits, rather, yeah, only consider these 3 bits, then what you'd want to do, and sort of put all the numbers into a set, we'll say, excuse me, then what you want to do is say, okay, for each number, take the XOR of these 3 bits, or with this, right? XOR that number with this mask, or, yeah, I guess with this mask, and check if that's in the set, right? And that means that this is a possibility. And you do that, it would take linear time, and so this kind of maximal amount is a possibility. And then if that's true, then, and actually you'd actually start with a full, you'd go from right to left. So you start with as many ones as possible, flipped, right? So okay, is it possible to get this, to XOR, to get this number? And which might be true or false, right? It could be that's the largest number, and then you could either get a 0 or 1, or rather, yeah, true or false. You can get all those ones, and then if you can't, then you would remove one of the ones, the mask, shift the mask down to the left, and I guess you would keep doing that. The problem with that, though, is there might be holes in that original mask where you know that none of the, either all of the numbers have a bit set to 1 in one of these positions, so it's not possible. So I guess you'd have to, I guess you do have sort of a caveat there where you have that full bit mask of all 1s, and then you just kind of, there's pockets of 0s where you would skip in the mask, where you know that it's not possible to get a value there, no matter what you do. But supposing that, suppose for a moment that all the bits are possible, just for a moment, that's kind of a small caveat. What you would do is you would say, okay, try to get like the largest possible number, see if that's even a possibility, by, as I said, by masking all of the numbers and then throwing out the bits to the right that we said we're not going to consider, and then put those into a hash set, and then for each number, check if the XOR with our full bit is in the hash set, right? Yeah. And if it's true, then that maximum possibility is possible. And now the thing that's odd about that is, what would we do from there if that's possible? Well, obviously if that's like the absolute maximum, then you're done. You can actually just return that number. You don't even need to know which numbers combined to produce that. However, let's say it's not possible, and now we remove a bit, right? So let's say we had, you know, like 1, 2, 3, 4, 5, and now we remove a bit, 1, 2, 3, 4, and we say, okay, we know we can't get here, but maybe we can get here, possibly. All right, so we do the same thing where we mask all the numbers with this bit set to 0, and you would AND this with everything, I think, with this mask, and then you would AND everything first, so that way all those bits are dropped, and then you would do an XOR where each number, you put every number into a hash set after you've ANDed, and then you do an XOR of each number with this mask and see is the result in the hash set. If it is, that means it's possible to get this as well. So if it's not possible, we would quote unquote continue. But suppose it is possible, or we did find a pair that it fulfills all these bits, then that pair is better than every other possibility, more or less. But the thing that's tricky is that it must necessarily be the case that that pair has to give you a 0 here, right? Because otherwise that pair would give you this, which is a greater number. Right, there would be a pair that could give you this. You would have already caught it. So it's not. So actually, this has to be a 0 then, really. Yeah. So I think you just. I think that's it. I think that's the solution. Because then you can just return this. So that means that those XORs can get you this. Obviously, you won't be able to get this. But what about this one? Maybe you can get. No, I'm sorry, I'm wrong. Maybe you can get. Yeah, I'm wrong. I'm wrong about that. Because I think there could be more than one of these numbers that gives you this. And let's say you have like this. Yeah, let's say you're here, right? Yeah, I'm wrong. I'm wrong about that. I mean, in this case, obviously, it has to be a 1 or a 0, but here you could have 1, 1, 1, 0, 0, and you have 1, 1, 1. You can't have 1, 0, or you already tested these cases, but you could have 1, 1, 1, 0, 1, right? And that's a situation where you'd have to check that, right? Because even though you found pairs that can get you here or here, you had masked off this value. So there may be actually a possibility where it's just this 0 that was removed. Yeah, so that's kind of tricky, I think. Not sure what to do about that. Excuse me. In which case you probably want to go not from right to left, but left to right. So if you can go 1 XXX all the way across, right, and find out if it's possible to get this, and then is it possible to get this, and then possible to get this, right? So now you find out how far can you go. From left to right. I guess in that sense you can kind of discover each bit one by one. So it's possible to get 1 zeros, right? Or either is or isn't possible to get that one. So it's either a 0 or 1, and then you know, if it's a 0, then you would continue with try to get the next 1. If it's possible to get 1 0 x all the way across, right? 0 1 0 0 1 zeros all the way across. Yeah, I guess you kind of just discover the most significant bits one by one, and that'll give you ultimately the largest number. You don't actually care, or you do care, but interesting. Yeah, I think you do it the way that I just described, where you build a mask from left to right, and you say, okay, the mask would start off with a 1 in the most significant bit, and then 0s for all the other bits. And you would say, if we first you AND this with all of the numbers, right? Or rather what you do is you take the AND of that with all the numbers and put that into a set. And then you take the XOR for each of those numbers in the set, XOR it with this mask, and check to see if that result is in that set. If it is, then that mask for that bit stays, and you go to the next bit. If it's not there, and you set that bit to 1, right? The mask, the next check, you're going to set it to 1. If it's not there, then you want to set that bit to a 0 and go to the next and end with the next one. Yeah, I think that's the way to do it, mechanically how it's going to look. And actually, at the end of it, the mask itself is what you return, because you're going to actually build a. You're going to find that there is basically there is some pair where this resulting mask is possible. Yeah. Hope that makes sense. It's a little confusing. I think it's what we do. So let me see if I can try to code that up. Maybe it'll make a little more sense when I program it. So yeah, definitely a little bit confusing. Yeah. So we go bit by bit in short. And we have a mask. Starts off at 0. We're actually going to return the mask at the end. We have a hash set of integers. Unordered set. And we're going to say target. We're actually going to go backwards, right? So 32. From left to right, the target's going to be 1. Bit shift to the left, I. I think it starts off at 31. If you bit yeah, it goes like this. And we go mask or equals target. Alright, we say for const auto x, or just, yeah, we'll call it int x nums. Go int new val equals x and the mask. Right, so actually we want to mask off all the bits to the right of what we're interested in, so just set those all to 0. The mask will basically always be 0 though, on the right side anyway. But we actually want, no, we want to do, yeah, let's do it this way. Mask to 0, current will also, we'll use two numbers to keep it kind of a little easier to understand, I guess, easier to yeah, easy, it was just easier to keep it easier. So the mask, right, kind of left to right, we're going to keep sort of appending ones, and so we know which numbers which bits we're considering. So yeah, new value and with the mask, everything on the right side will be zeros. You can also then you can do then you can say current, right, current or equals target, and we're going to vals.insert. So first off, vals.empty or vals.clear, right, remove everything from the values. Insert this new value, this masked value. I'm going to say bool check equals false. Say for int x and nums, int new val is x and mask, new val equals XOR equals the current. Say if vals dot call that find, that's what it is. If, or actually you do count, vals.count of new val, it's non-zero, check equals true, and break, right? And then we say if check, so we found our value. If not check, we want to say if not check, then current we're gonna target. We're gonna set that to a 0 for that target, for that spot. Not possible, or other bit position must be a 0. Yeah. Optimal solution, yeah. Call it the optimal solution, right? So that's basically the idea, encoded. Does this code run? Oh, that's right. Nice. I think, did we get it? We may have gotten it. I don't know. Okay. By the way, this could also be, I don't know if you need this edge case anymore, just as an aside. I think it'll handle that case properly. Yeah. Okay, I think we got it. Hopefully I could explain that. I'm not even sure if I could fully explain it. My thoughts on this. Kind of awkward to explain. Okay, I think we're right. I think we got it. How long did that take? It took over an hour. Ouch. Ouch. We don't really need to address the edge case. So, yeah, pretty interesting. Basically, we use this. We go bit by bit. We use this unordered set, and we say we try to discover using a bit mask on all the numbers, like what the most significant, we want to discover the most significant bits that are possible in an XOR through this set of numbers, sort of bit by bit. That's pretty much what we're doing in English, plain English. And we're using some kind of clever, not clever, but just different manipulations to do that, to achieve that. Yeah, I think we got it. I don't know. Let's just throw in some random inputs. Don't mind me just mashing the keyboard here. I think they're all positive numbers too, right? Positive numbers. Invalid test case. Nice. I think we should go for it. I think this is it. It's about as good as it's gonna get. Yeah, let's go for it. I'm afraid to go for it, but let's go for it. Hey, we got there. Sweet. Wow. We're not very fast though. We're linear time. We're pretty slow. We're only faster than a fraction of the solutions. That's kind of interesting because we're 0 milliseconds for some of these. Interesting. Huh. Why, really? I thought I was so clever doing this too. Excuse me. Really. We're so slow. We're so slow. Oh, we did it. It's linear time. We got there. Huh. No kidding. Well, yeah, I guess dumping all of the numbers into an unordered set 31 times, somewhat inefficient. Is there a more efficient way to do this though? Huh. Oh no. No, I'm trying to do this more efficiently. Uh-oh. Excuse me. Oh boy. Well, I guess there's one thing we could do, which is go like do this kind of thing. Bit shift the target to the right one. Try that. Oh. I was just wrong. No. Uh-oh. Uh-oh. Oh no. Really? No? I'm so confused. I don't. Why would you can't do that? What do you mean you can't do that? Excuse me. Excuse me. How about that? That doesn't work, does it? No, it doesn't. I think this has to happen afterwards. Is that what's wrong? Too many times being shifted? No. What? Why does this work before but doesn't work now? How does that make sense? I don't understand that at all. I don't know what happened here. Now, how does that work? I don't get it. Huh. What? What? That's a pretty small optimization I think you could make. It doesn't give you very much, but it does make a small improvement, I think. Yeah. One bit shift to the left 31 times. That's the initial target. That's true. And then you just bit shift it to the right each time. I think. Excuse me. Yeah. Why can we not just bit shift it to the right? One element. So confused. Clearly don't understand something here. Excuse me, and the test should be excuse me. Oh, thank you. Thank you, Mr. Compiler. Oh, that's why. Gotcha. Has to do with the sign. I see. That's really annoying. Right. That's really annoying. I see what's going on there. Because these are unsigned, these are signed integers. You can make them unsigned, I think, right? Do the same thing. I don't know if it'll be the same thing. It's a little different when things are signed or not signed. I kind of try not to mix and match signed and unsigned things. Definitely gets a little confusing. No kidding. So that's why. It's because if you bit shift to the right, it'll maintain the sign, the thing that you're working with. Again, all these numbers, these are all positive integers or non-negative integers, so unsigned is fine. However, it's tricky, I guess. Okay. Yeah. That is a very subtle thing, but it's there. Does this hold for all cases? Okay. Not much better. Not much of an improvement. Slight improvement, I guess. Great, I suppose. So. I'm gonna have to sit down and think about this for a while. How to optimize this and make this faster. This is quite a bit slower. Right, because we're building this unordered set every time. I think that's extremely inefficient. Not only is it inefficient, but also you don't need to do it twice. Right, so we're kind of doing this twice. You could actually combine this into one pass. So you could do bool check equals false. So let's do it this way. like this. We're going to copy it. And put this into one set. So, or one pass. So first we clear the values, set our check to false, create this new value, say if, we'll do perform our check here, right? So we'll say new val current. So we'll say count new val current, and if we found this value, it's already in there. If so, we have this new value, and we have all this with the mask. We say if we XOR this new value with what we're currently building, that our check is true, we can break right there. Otherwise, we're going to put this new value into the set. Yeah. Let me perform our check. So something like this. What does it look like? Okay. Is that true? There we go. That's a lot more efficient. Yeah, you don't need to do two passes with this. It's definitely a lot more efficient. Just go one more time. Try again. That's a lot better. All right, 60%. A lot less memory. Definitely a lot less memory. A little bit more efficient. Quite a bit more efficient than our previous solution. Yeah, much better on memory. A little more efficient. Now the question is there a way to do this even more efficiently? Yeah, because this mask and this current and this target, you don't actually necessarily need to manipulate these things in this way. I'm actually not sure if there's a faster way to do this. The check even, you don't even need to do this check either, you could just do this. Oops. Actually, that's probably what makes this more efficient. You don't even need to do that anymore, do you? I think so. Oh no. Uh-oh. Wait, this works? But if we move this check, oh, not check, that's why. Oh, I see. Oh, I see, okay. Gotcha. Right. Oh, I see. Check is true, we can break. Otherwise, oh, maybe I do need to do it this way. If not, check. I see. Yeah, there's a tricky thing there where basically this says if you don't find it, then we're going to undo this part. But if you do find it, then we're going to keep it. Let's see. Yeah, I mean, yeah. I want to remove this if I want to make this smaller, this part. I think this will speed things up a lot if I can remove this if statement at the end here. Let's see, just think. I actually don't think there is a better way to do this, or there might be a better way, but I'm not seeing it. I thought there would be a better way, but I don't think so. All the different approaches I'm considering, it's probably the best. Because basically this sets what you're looking for, I guess. You XOR with the target. By the way, this could also be this, doesn't really matter. And then you would clear that element. This is tricky, man. I don't know. It's tricky. I don't know. Trying to optimize this somewhat. Not obvious how to do it. Yeah, there's got to be a somewhat more concise way of doing this. I'm not seeing. I want to say you could remove this if statement here. I don't think this will speed things up at all, but I'm wondering if you can do this. Not really. Doesn't really do anything. Because the reference itself is going to be an integer, I think. So it's not like it really matters. You know what? Wonder, what's in the wonder ball? What's the wonder ball? Actually, you can change this too, by the way. I think that also works. As an aside, I think this technically will also work. Hey, okay. Not sure if that's much better, but slightly better. Oh, another slight improvement. Didn't even think about this. Because these are unsigned integers that are only being used for positive numbers. So you can optimize things just a little bit more also. And actually in that case, you can do everything to be ints instead of unsigned ints. Doesn't really matter. Didn't really think about that either. That might make things even faster still. That didn't seem to speed things up very much though. A little bit faster. Oh, okay. One less extra loop here. Yeah, still correct because these are all, as I said, they're positive integers that are. I mean, you could make all of these unsigned integers too. You could do that. I don't know if that'll. Shouldn't matter. I don't know if that makes a difference. Maybe. Maybe. Assumption here is that oh, okay. My assumption here is that it's easier to work with unsigned integers than it is integers. Does it still work? There's two assumptions. One is converting between unsigned and signed integers. Like if you could skip that conversion, that should be faster. And then also, I'm assuming it might be easier to work with only unsigned integers, only because these seem to be a little bit faster when we were using unsigned integers. excuse me. So yeah, doing one less loop is a little bit faster as well. Cutting out that that extra variable in here is also a little bit faster. Truthfully, I don't know of a way where we can make this one loop. Like remove this if statement at the end. Huh. Could do something like this. I don't know if this is better though. It seems like it's not better. Well, it does avoid this this branch here, which I think in theory is better. Alright, let's go for it, see if that works. Okay. Not much better. Not much better at all. No. No. I don't think it's better to do that. I don't think so. No. And somehow making these unsigned, I think, made things a little bit easier. Make it everything unsigned. Somehow that seemed to make things easier. Or faster. You signed. Unsigned, you signed. No, not really much faster. Not really. I don't know, man. No. No, doesn't really. No. Alright. We're like 45 minutes into just trying to optimize things. We got some improvements, so we were at like 456 at the max for the fastest, or the slowest, and we went down to 76 at some point. It's like 5 times, 6 times, 5 or 6 times. So that's better. Still pretty slow though. Still not like fastest possible. May not actually need to do this either. Maybe that's part of it. That seems kind of questionable. Yeah, okay, you do need to. I was gonna say. I don't think. I think you do need to do that. I'm curious if there's a way to avoid the mask, changing, how we manipulate this mask. Kind of wondering about that. Instead of slowly building this mask, we can do could do target -1. and then invert it. Flip the bits. I think this is the equivalent to the mask. Yeah, let's see what we get. It's still correct. It's not really much better to do that. That was faster. Gonna remove that. Oh, didn't mean to do that. Gonna remove that. Okay. Maybe a little bit better. Not much better though. Something of an improvement in some cases, sometimes. Huh. I don't know, man. I don't know what to do. I mean, we got the linear time solution. It's relatively quick, all things considered. Not perfect though. What are we missing is the question. I'm wondering if like one or two of these operations are not necessary. Something in here. Or maybe there's a way to do this without using the... Excuse me, maybe there's a way to do this without using the set. I don't think so though. I don't know about that. That seems kind of hard to do that without using the set. I don't know, man. That's probably the best I got. Let's see. Let's take a look at the discussion. Yeah, I don't want to waste too much time trying to figure this out. How to do this better. Let's see what the discussion's got. A try. No. No. Without try. How do you even think of getting it? Haha! I got it. Awesome. Sweet. 85%. Array partitioning. Whoa. Alright, without a try. Max, mask, set, SE. Oh, yeah, no, actually this is what I did before when I said you don't need to use the bit. Hold on, if we go this check that I was doing, so yeah, I set it each time. Well, you could technically, you could do something like this. Maybe it's better. Let's try this. Maybe this is better. It's kind of what he did. That's kind of what I thought of already though, which was new current is going to be current or target, and then new current. Yeah, just leave that where it is. Something like this. Okay, but not really much faster, is it, right? Because you got to create this new value anyway, you know. Not very much faster. Yeah. I think it's actually faster to do it the other way. Oh, okay, 80%. I don't know. Sometimes it just rolls well, I guess. 76% again. Kind of random, huh? Yeah, it seems to just kind of roll randomly, however, how fast it's going to be. These improvements seem kind of minor. Excuse me. I guess this is a little more concise. Excuse me. A little easier to understand. That's pretty good. Almost 90%. It's pretty quick. Pretty quick. Yeah, I mean, technically you save yourself some operations doing this. Also. It's kind of what I was doing before. It was like just have this mask variable over here. It's kind of random. You could do It's kind of what I was doing before. Is that faster? I don't know, maybe. I think it's actually faster to do the flipping over the target and subtracting 1. I want to say somehow that's just really fast. It's even faster than even performing that operation multiple times is still faster than doing these other things with the mask. Yeah. Somehow it just seems to be fast to do that. Which is kind of weird. I don't know. Could not tell you. Why is this faster in some cases, slower in other cases? I don't know. Who knows? This doesn't seem that much. I don't know. That's arguable. It's arguable what we do with this sort of bit manipulation thing, these bit manipulation things here. I really don't know. Alright, we'll get to the other answers. I think this is cleaner. I like this better. How to try? Yeah, that's kind of what he did. What I yeah, similar, very similar thing. Oh, this is extensive. This is lengthy. Simple solution. Also gonna stop scratching my nose here. Oh boy. Ooh. Okay. Find maximum XOR. Max XOR. So he has this get max XOR routine here. It's 2 sets, I minus 1, position, set 0, set 1, set 0, list 0, set 0, okay. Excuse me. Oh boy, what is this? What is this? How fast is this? That's the question. Is this faster than my result, right? My solution? Probably. Yeah, using unordered sets is kind of slow. Let's just grab a solution and see if it works. How fast it is. If it's not very fast, then I just won't bother. Alright, I grab the whole thing. Let's go back actually. Okay. Did I lose all my test results? TLE. Nice. Interesting. So no. No. Does this work? How fast is it? Not much faster than mine. Apparently you can use a try to do this. I think what I did is still better though. I'm using the try. What is this? Okay, apparently this is quick. Whoa! 98%? Okay. It's not my solution. That's pretty good. 22 milliseconds, 99.5. Whoa. How about the try again? Wow. It's pretty slow. The try I don't think it's that great. This is interesting though. I don't think you need the unordered set anymore either. Huh. It's not that much faster than what I did. I mean, it's definitely faster, but you know, I was in that range, that 80 milliseconds, 70 milliseconds. Not most of the time though. It's very interesting. I think I like mine better though. I think it's easier to explain. This is kind of a bit of a to do. Yeah, pretty fast though. Somebody did it really fast. Somebody had like 100%. I don't know, man. This is definitely faster than mine though, considerably. But I think as far as like how quickly and simple it is to explain in code, I think mine's a little bit better. I think it's a little bit better. Maybe? Maybe I'm wrong, I don't know. Short version. By the way, you can do, there's a quick sort partition that you can do using nth element using quick sort implementation. It's built in that you can use. Yeah. Don't necessarily need to write your own. Although it's not too isn't not too bad what he wrote here. Short version. Interesting. Put mine back up. We'll go ahead and put mine back up. I like mine. I think mine's pretty good. I don't think it's the best, but I think it's pretty good. Yeah, 212. It's kind of slow. Oh wow. Suddenly consistently slow. Yeah, so you got that a few times too. It's definitely slower than the other approach. Quick, so what is this? Okay. Working with the most significant bit on the left towards right. The more significant bit is 1, the XOR value is greater than those with this bit equals 0. Similar to quicksort, partition a certain range, of the array numbers in place. Left subrange as current bit equals 1, and the right subrange as current bit equals 0. Let's name them as A and B. In order to find the greatest XOR value, we have to take one number from A and one number from B. And to set next bit to 1, must be a subrange in A and a subrange in B having opposite bit. Otherwise, next bit will be 0. So we partition range A and B recursively. When partitioning range A and B, there are three cases. A has both 1 and 0 ranges. We check whether B has bit 0 or bit 1 range or both. A has only bit 1. We check whether B has bit 0. 3 has only bit 0. A has only bit 0. We check whether B has bit 1. I don't really understand. For every recursive call, the runtime is linear. There are 31 levels of calls, linear runtime, extra space is constant, code works in place, code with comments as below. Whoa. This is definitely a lot better than what I wrote. If it's true. If it's true. Interesting. Very interesting. Here's a helper function. LSLE, RSRE, two ranges of numbers. Gives a max XOR value to the current bit. Bit decreases from 30 to 0, working from most significant bit on the left towards the right. Similar to quicksort, partition LSLE to two ranges, LSJ-1 and JLE, by swapping elements. The range on the left with current bit equals 1, and the range on the right is 0. Do the same to RSRE. Order to set the current bit in the answer eval to be 1. The left LSLE and right RSRE ranges must have subranges with opposite bit. If so, val equals val bit shift to the left 1 plus 1, otherwise val is val bit shift to the left 1. Interesting. Huh. I don't understand this at all. Not even remotely. This is similar to what we were thinking about doing before. What's interesting about this is you don't necessarily need a excuse me. Don't necessarily need quicksort. Like, this kind of has nothing to do with quicksort. This is this is just sorting on a particular bit, a more significant bit. Right, and so I guess, interesting. I think I get it. So what I had done was was somewhat a little more forceful in that, or required a little more resources than necessary, in that we checked to see if went bit by bit to discover whether or not there exists, whether or not we can get that particular bit by masking all of the numbers to only the bits we're interested in at the time, and then XORing those remaining bits with what we are currently interested in, right? So, right, so we have this kind of, I guess maximum value that we want to obtain with these bits. And so we XOR that and we say, okay, so first we have this new value, this masked value, and then we have a set of those masked values that we've already considered. If we XOR what we're looking at, this masked value against what we're trying to get, and check if that's in the set already, that means that we have a pair of numbers, two different masked numbers, that when you combine them, you XOR them, it'll give you this maximum that we're looking for. So that would affirm that the maximum that we've currently built is possible. And if it's not possible, then that means that particular bit that we added, sort of the most significant bit, or not the most significant bit, but the sort of next bit of consideration, I guess. That means it's not possible to set that to a 1, so it's got to be a 0. And so we continue building our number, the sort of maximum OR that way. The part that is unnecessary, is the machinery to discover each bit, as described from this person who was talking about sorting. You could actually sort your numbers in place based off of the most significant, or particularly that bit of consideration, and you could just check to see if after you're sorting, whether or not the numbers are whether or not there exists, I guess, in a particular range, a pair of numbers such that one of them is a 1 and the other one is a 0. Yeah, a little more involved though. Like, I don't fully understand it. I would have probably coded this way if I saw this. So I don't actually see it yet. Excuse me. I think I get it. This kind of goes back to what I was saying before about partitioning into pieces and then trying to kind of make the jump from one partition into like sort of the next bit. I guess, yeah, jumping from bit to bit. And the partitions required. So I guess the first bit you would partition on the most significant bit, and you'd have a sort of a sorted list of all the numbers that have a 1 in the most significant bit. I guess we'll say they're on the left, put them on the left side, and then on the right side we'll put all the numbers that have a 0 as the most significant bit. And then now we know that we can get an XOR of at least that most significant bit. And now we consider the next bit. We say, okay, of the numbers that have, I think both ranges you would sort then. You'd say, of the numbers that are most significant bit set to 1, and the numbers that are least significant bit, we're going to sort each of those ranges, I guess, internally. Excuse me. On that second most significant bit, or the next bit of the next bit. So those two sub ranges, or those two partitions. Now we sort those using a stable sort. And then now we would have 4 different pieces to consider. We have on the left side two pieces that the first bit is the most significant bit, is set. And on the right side, 2 pieces also that have the most significant bit is set to 0. It's not set. And then within those 2 pieces, right now there's 4 pieces. Those are sorted with the most significant bit, or the second most significant bit, right? The 2 subranges are going to be sort of 1, 1 on the left, 1, 0 is the next subrange, and then 0, 1 is the next subrange, and then 0, 0 on the right subrange. So I think what would happen is if you can sort of recursively sort this by I guess each bit and then what you'd end up with is, I actually want to say you could just sort this from left to right then at that point. It's actually the same thing. But obviously a normal regular sort gives you a sort of sort in decreasing order. A normal sort would give you O of n log n time, although you can use radix sort or something similar to make this a linear, counting, no, not counting sort, but radix sort would work, right? Because you could sort on the bits. But you could also, excuse me, oh, I didn't think about, actually, that's kind of funny. There are other questions related to, I guess, sorting, we'll say, that I didn't really think about it, but you could actually use a radix sort. Yeah. You can use a radix sort on the bits to give you a much simpler solution for linear time solution. There are other questions that I've seen in the past that were like, if you could sort it quickly, then it would be a lot easier, but it's kind of a hack. Excuse me. So, yeah, so I think if you just radix sort this, you'll get the same result at the end. But the issue is whether or not a particular range exists when you do this sorting. And for instance, like 1 1 1 0 0 1 and 0 0, there has to be, in order for that bit to be set to a 1, that the correct ranges need to exist, I guess. So, for instance, for a 1 1, the other range, the complementary range, is 0 0, and that has to have something in it. And similarly for 1 0, the complementary range is 0 1. And actually that sort of range complement notion, that idea, continues at each level, right? So you only need to consider the previous range. You don't actually need to consider like the whole tree, I guess, of things. So like, let's say you do find something that's in 1 0 and in 0 1. Now you want to see the next round of things is, right, sort of 1 1 1. Well, there's a bunch, right? There's sort of I guess I think we did this before, right? It's 2 raised to the b minus 1. So if we have 3 bits, that gives us 4 possible sort of range combination, range pairs that we would be interested in order whether or not we can set this bit. Set this next bit, and I actually don't know, now that I'm thinking about it. Excuse me. I don't know. Yeah, I really gotta sit and think about it for some more. Think about it more. Let me do that. Let me take off my headset too. Just kind of lay down. keep thinking about this problem, and I'm not really making too much progress thinking about it. I think what I'm gonna do is take a break. Well, I'm gonna take a break. I don't really know. Or you know what? I'll just read this explanation again. I was kind of trying to ponder it, but I'll go full screen for a minute. Yeah, do it this way. Hold on just a moment. Yeah, so I pretty much fell asleep when I laid down. Didn't really think about this too much. I kind of struggled to understand. So, yeah, I kept trying to think of like how this could work, but I actually don't understand it. Don't get it. I think we'll just try to get an understanding of what the answer is. Explanation. My thinking was like, oh, maybe it was something along these lines, but I was like, there's something along these lines, but I kind of got stuck on if you had like 1 1 1 1 1 0 dot dot dot. Actually, no, we'll do. If you had something like 1 1 1 dot 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 1 1 0 dot dot dot, basically have 8 different kind of possibilities here. And so on. Actually, there's only 1 2 3 4 5, only 5 of these, still 3 more. The problem that you have, the problem that you run into is it's not so obvious to me how you kind of map each of these ranges back to each other. Like the deal is you have this. Let me actually do this. Make this a little bit smaller. One, two, three, 4, 5, 6, and there's 7, 8. And basically, there's a map. You want to connect these to each other, these ranges, in order to exactly what we had before. In order to so you can sort your numbers in this way, and then in order to confirm that a particular bit is possible or not possible, right? If it's not possible, then none of these pairs will exist. But if it is possible, then you'll have at least one of these pairs exist. And I got kind of stuck on that because this 111 over here does actually depend on the previous bits. You know, it actually depends completely on these previous bits. Yeah. These previous two. In order to know like what range you're looking for or looking through. And really it's just an existence of each of these ranges, right? So like, yeah. So you kind of just need, 1 dot 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 and then 0 dot dot dot. And if these two ranges exist at all, then this first bit is a possibility. And then if you had 1 dot 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 and 1 0 dot 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 and 0 1 dot 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 0 0 dot dot dot, right? These are obviously both subranges, but the pair of ranges goes like this. And then again, each of these have subranges. Again, you could split each range into two. Each time you would sort on that sort of most considerate bit, or the next sort of bit of consideration. But like I said, the issue is like how do you map these to each other without correctly mapping connecting these to each other. I guess doing it recursively, because it's sort of on a stack, you can kind of know. Yeah, I guess using the sort of recursive stack, you can get you can kind of map these back to each other. Maybe that's the way you do it. But it's definitely not so obvious to me how this would be done. So I guess we'll read this again, try to understand. Most significant bit on the left towards the right. The most significant bit is 1. XOR value is greater than those with this bit equals 0. Really confused by this, but okay, don't really understand. Partition a certain range of the array nums in place. The left subrange has that current bit 1, the right has current bit 0, let's name them as A and B. In order to find the greatest XOR value, you have to take one number from A and one number from B, and to set the next bit to 1, there must be a subrange in A and a subrange in B having opposite bit, otherwise the next bit will be 0. So we partition A and B recursively. Yeah, so there's two subranges, right? So there's sort of AA and AB, and then BA and BB, let's say, something like that, these ranges. Partitioning range A and range B, there are three cases. A has both bits 1 and 0 ranges, right? So there's AA and AB. Check whether B has both, or one or both. A only has only one bit. Check whether B has bit 0. Only one bit. B has 0. A has only bit 0, and check B has bit 1. Okay, so we do check all four cases, I guess. Yeah. Basically, really you're looking at this then, this picture. And you're just going to say if A has 1 bit, then you want to check if B has 0 bit. If A has a 0 bit, you want to check if B has a 1 bit. And if this has both, then you check if there's either of them. And that'll tell you whether or not that second bit is going to be flipped. And if you can't partition the range into A and B in the first place, then obviously that bit first bit can't be set, but then this is how you figure out if the second bit can be set or not. And the problem with this though is, excuse me, I guess you're doing, the thing I'm confused about or uncertain about here is that I'm wondering if you need to consider these sub-ranges like at the other levels, the lower levels. Hopefully that makes some sense. So like, or actually, I don't know. Apparently you don't. Apparently you only need to consider what this person said here. But my thinking is like, what about the next value, the next bit? Do we only need to sort based off of the second bit, right? In which case you would then have, you know, doesn't matter x, the second bit would be a 1, ... and then second bit is a 0, and then sort these two ranges in the same way. So 1, 1, ... 1, 0, ... 0, 1, ... 0, 0, ... and then you have the same logic, right? And now these are only sorted on the second and third bits. Right, this would partition the entire range. The deal is, it's possible that even though this checks out, so I really need to use the bathroom. It's possible that even though this checks out, you don't have, hold on a second. Excuse me. So it's possible that the pair that justifies the second bit being set, let's say you do find one of these pairs, it's got to be within that same range, like within this same set of possibilities. Like this has to become the new quote unquote A and B, I guess, to operate on. And then these two sub-ranges need to be split again. So I guess that's interesting. So no, you don't do it this way. This is actually, yeah, that idea is wrong. No, you actually, if you do repeat on these sub-ranges, right? Recurse on them. So these become, so if it's this one, then you have 1, 0, ... and 0, 1, ... and you split these again. So 0, 1, 1, ... 0, 1, 0, ... 0, 1, 1, ... and 0, 1, 0. And you're doing the same thing where you want to pair these off and pair these off. And if it's this pair, so that's sort of, you do the same thing again. 1, 1. Right, I see. ... We'll just, I'm not gonna rewrite it. Okay, I think I get it. So yes, so each of these subranges, you can split your range into two pieces and perform that same check on sort of that next significant bit that you're interested in, and that'll tell you. Yeah, I think the way it works is, I guess, let's say, suppose we first split into ones and zeros initially, right? Just do that initially. Suppose that for a second. Now that we have these two ranges, then we split each of those into two ranges, and we check those different cases, right? There should be four. There are a few different cases to consider, but really there's sort of just two cases where, you have range AA and BB and range AB and BA, and you kind of combine those two ranges. If they exist, then you set that bit to true. If neither of them exist, then you set the bit to false. But if either of them do exist, then you recurse I think on both of them, actually. Yeah, and because both of them should split the array. Like even if you recurse on both of them, it's still a linear amount of operation on the whole. I think that's the deal, because now you have sort of a tree of things that you're operating on. It's still a linear total number of operations. So each bit you operate on is still a linear amount. But now that you have these two subranges, then you can repeat the same thing you just did on these first two subranges. So you split into 4 subranges and operate on pair off these two subranges. And if either subrange exists, then you flip that bit for that position to true. If neither of them exist, then flip set to false, and what you're going to do is actually skip that bit. Set that bit to false, and if neither of them exist, then you go to the next bit to consider, and you'd kind of start again from the top. So just thinking how to do this. It's tricky. So really you split on two pieces, right? So you split on one bit. I guess, yeah, your range, you split on one bit, and you kind of just want to return the ranges, right? And whether or not they're empty. I think that's the way to do it, right? So you return two numbers, I think. That gives you two. So you have a split that returns two ranges. It's really a sort. It's not even a split, but yeah, sort, split, sort, however you want to express it. And it's stable and in place, right? In place sort. And then it doesn't even really matter if it's in place either, because we'll just say we can use the nth element sort, which is the quick sort from the partition from the STL. That's fine. I think I'm starting to understand this. So we would nth element to sort these, and then we would say if it's not off the edge, right, for the 0, or if there is something, if they're both non-empty, the left and the right subarrays, then we set that bit, that position, to a 1, and then we recurse on the left side and the right side to get the respective ranges. And so or just say quote unquote recurse on the left and right side, I guess. Trying to map out the logic here. So we would get the left the split, or really it's the split point is what it is, I guess. But yeah, we have a range. So there's sort of a left endpoint and a right endpoint, and then this sort of the nth element will end up being the split point. And we want to say, right, if both sides exist, then we can set that first bit, and then we're going to recurse again on the left side and the right side, incrementing to the next, taking a look at the next bit, and whether or not we set that next bit is going to be if AA exists and BB exists, or if AB exists and BA exists, right? Now comparing those two different split points, so we could sort of figure out if these exist or not. And I'm wondering, I want to say we want to just use have a subroutine that tells us whether or not yeah, I guess the subroutine that'll sort and split on a particular bit on a particular range, right? That's fine, I think. And then the recursive part, I guess for the first bit, you would just split once and then check, and you kind of keep iterating until that you keep iterating through the bits until you get at least one bit where that works, and then from there, so I guess you'd have one routine that kind of just scans through until you get a significant bit. Then the next routine, and you'll keep setting your bits accordingly, right? If they're, if you keep splitting and there's only, everything kind of ends up on one side or the other, right? If your split point is just kind of, or the left and the right sets are always empty. Then once you're not empty, then you can say, okay, we're going to have another subroutine which we're going to operate on the left side and the right side and compare AA and BB and AB and BA. And if either of those exist, then we'll set that bit accordingly. And on each of the ones that do exist, we're going to repeat, recurse this helper, I guess. And see, that's things get interesting there. A certain recursion of some kind. I'm not sure exactly. Let's say call it a different routine that we'll call. So there's different. So some routine that we call when we know we've got a split and we want to split that again on those both sides and have AA and BB and BA and AB. Excuse me. And if either of those exist, doesn't matter. Both of them or either of them, either one. Both of them, right? If neither of them exist, then then that bit is set to false, and I think we just go directly to the next bit and sort. See, that's the thing. I'm pretty uncertain about this logic here, like how this works, how this is gonna work. Just the coding of it, and also I really need to use the bathroom, so I'm a little bit uncomfortable at the moment. Yeah, you kind of want to use some degree of recursion on both of these that work. So if neither of them work, what do you do? Well, that bit would be set to 0, that position, and then what? You want to go to the next bit, and you would actually want to, like, things would still be sorted the way, like, you don't want to lose your position in the trying to think here. let's say we're looking at exactly this picture. 1, 0 works, so we have a 1, but none of these work, so we have to have a 0, right? I think on each of these, so actually because none of them work, it means that you either have only one side here, or because you have a 1 and a 0, that means that it has to be basically one of two cases, right? It's either this one and this one, or this one and this one. Right, that's the only way that this doesn't work. And so actually, yeah, so if it doesn't work, you do still have two ranges to operate on. But they're so basically that second bit is set for everything. Interesting. And you could effectively skip it and go back to this go back here, right? It's pretty much what that means. Yeah. You kind of just iterate again from here. Again, you would have the next bit, which is then split your ranges. It would actually be the same sort of sort that you had before. That basically this didn't do anything when you consider the second bit. It didn't change anything. That's pretty interesting. So, right, okay. Pretty much means that the second bit is present for every number. That particular bit is present in every number. It's gone in every number. You either have one or the other in that case. And it can be pretty much ignored completely, I guess. Yeah, you would just repeat on the next. You would just go to the next bit with the same ranges that we were just working with. That's if it fails. If it doesn't fail, then you set that bit to 1, and then you have one or the other of these, right? Or you could have both. I'm just thinking, if you have both, then you would kind of want to just keep recursing. Except you'd want to modify the range that you're working with now to only include, well, yeah, I guess the ranges that you're operating on now changes to only include sort of those parts, and it would kind of go back to like as if you were looking at this part. Look at the next bit and split those ranges and just pretty much do exactly the same thing you just did. Do it on both of these, I think. And the thing that's tricky about that is basically you've pretty much split the set of, even though you're still sorting on the same array, you've split the set of numbers you're considering now into two pieces and recursing. So it's almost like a full recursion on those numbers, just with I guess a different range. The reason why it's awkward to call it like a full recursion is that the original routine doesn't have two ranges that you're operating on. The first routine actually has one range that you're operating on. So that's why it's a little bit awkward. I want to say something like this first pass where you split is really sort of like the degenerate case where you've just skipped a number. And I think this is kind of the only situation where you really only have one range to operate on. So it's a little confusing. It's really confusing. But they handle that. They talk about this, right? They talk about having, well, there's really 4 cases, I guess. Well, I gotta think about this some more. I could really gotta use the bathroom too. I think the solution I came up with is pretty good. It's pretty quick and it's like kind of simple to understand in code. Whereas this is like really kind of hard to understand. Maybe this is a little bit different than what they're actually doing in the other explanation. Maybe that's why it's kind of hard. I'm kind of struggling with the recursion, I suppose. Yeah, because really you'd have sort of 2 sets of numbers defined by a range over the sorted list. And that's sort of what gives you, that's sort of how you go from here to here, right? You have these two ranges. That could be done recursively. The thing that makes it awkward is operating on 2 ranges or just 1 range, right? Because if you could have a case where you try to sort and right, and again, like, so you sort on this bit 1 and 0, and none of the elements actually have this bit, so it's all 0, or all of them have this bit, so they're all 1s. Then you'd want to set that bit to false in your output, and then move to the next bit. And that can happen, and that's also you end up in a similar position again where you only have 1 range to operate on. Yeah, I guess these subroutines you end up with. That's confusing too. I'm trying to understand, like, in a kind of a divide and conquer approach, I guess. It doesn't necessarily need to be divide and conquer, because that's kind of what this ends up looking like. So this looks like sort of like a divide and conquer recursion. But each level, I guess, would represent like whether or not you flip a particular bit position on or off. And I guess you would just, you have to have something kind of idempotent, right? So if it starts off at 0, and then if any of them check out, then it flips it to a 1. Yeah. However, you could run into a position where you could run into issues where see, I don't think that really makes sense either. Like you could run into a position where some set of these let's say something like this set here. If you process it, this green one, you get 1 1, and then all zeros after that. But this set over here, you would get. I want to say something like you get 1 1 0 1 and a bunch of zeros. And this other set, you get 1 1 0 1 0 1 0 or something, or actually better, it would be 0 1 0 0, right? And now you actually would need to take the best of these, which is this one, but you wouldn't want to take like an OR of these, which would look like this, which would just be wrong. If that makes any sense. So, because that's kind of, I'm trying to ponder like, how do I reconcile the results of each of these? Because I'm trying to avoid every call returning another XOR number, I guess. Although maybe that's what should happen, actually. Maybe every XOR call should have another number that it sort of modifies and improves. And like really what you'd end up doing is you would say, okay, from this range, you have this first bit is set, and then now you're going to call. So that's the thing, is like it's not like a recursion on each. It's not exactly divide and conquer. It's like a you call some subroutine on the left side and on the right side, and then you kind of reconcile those things to set the next bit. I guess you would pass to eat. You do a recursive call that involves two ranges, where you would actually give to that as a parameter. You would give it sort of a current maximum, I guess, or current XOR value to each of these calls, where that second bit is flipped to true. And then each of these calls, these recursive calls, would presumably return a value, and then you would compare those two to each other, and you take the larger of those two. I think that's kind of where the recursion, kind of how you'd handle that, or how you could handle that. And so each of those calls would sort of have a bit set, I suppose, in a number that it would kind of modify as you go. A little awkward, a little confusing, but I think it's correct. I think that's how you would do it. And then there's still this issue of like, how do you handle the top level when you only have one range, like in the recursion? Because that could come up in some places. Like if you, let's say this doesn't exist at all, then you have this set of numbers where that one is set properly, but then this one, actually this would just be 1 0, right? If this doesn't exist. So you don't even care. You don't care about the one that doesn't exist, right? If both of these don't exist, then actually it's the same exact position you were just in, except you would recurse now, and then you'd use the next bit to split these ranges. So I think the 2-range recursion is not really a big deal. And just think. Sort of. I don't know. I don't know how to code this. Yeah, 2-range recursion. Depending on what you get, you would return the larger of the XORs that are returned. You'd also want to give a set of bits, right? For each of these pairs, a bit set, and you also want let me just see. Sorry, just messing around with. The single range routine, I think, is different from the double range routine. That's kind of what I want to say. The double range routine, I think you can do this recursively, and you would say you have some bit position that you're interested in. You'd split these two ranges based off those bits, collect what you have, right, into these two pairs, and you'd recurse on whichever pairs exist. If none of the pairs exist, if both pairs exist, then you'd recurse and you return the larger XOR value of both those pairs, and also both those pairs you would kind of update your bit set that you currently have with the next bit for each of those. If one of them doesn't exist, obviously you just default to the other one. You don't operate on the one that doesn't exist. If neither of them exist, then you'd actually run the same. You'd end up running the same routine again on 2, but with the next bit. So your bit set would update to a 0, and you would just call the next bit. Now, obviously, you only need to consider one of these. That if one of these exists, you don't need to consider the other one, because the bit set we know is gonna be a smaller XOR value, so we don't even need to consider it. So I guess part of the function call is whether or not the pair exists. I don't know. I'll have to kind of sort that out, the logic there. Yeah, given that the pair exists, on both sides, give it the pair exists for both sides, then you would recurse on it with the updated bit set, and then either you wouldn't recurse if it doesn't exist, and if you don't recurse, on either of them, that's an important case as well. That's kind of like the 3 cases that were being described, where neither pair exists, or one pair exists, or both pairs exist. If both pairs exist, we recurse on both of them and return the best of the 2. If only one pair exists, then we recurse on just that pair, return the result of that. If neither exists, then we go to the next bit, split on the next bit, and try again. I think you could write like a sort of a while loop type of thing, or a while loop until one of these pairs exists, and now the thing that's tricky about that is if we go through all the bits and neither of them exist all the way through, then we want to just return our bit set. However, if any of them do exist, then we want to recurse and take that maximum. And we could just take have like a maximum outside the while loop that's is originally our initial bit set here, and the bit set when we're given 2 pairs, and then perform the while loop and then just return at the bottom the maximum, and the maximum could just be defaulted to this initial one. And so if there's nothing to recurse, then we never update that maximum. So then it just defaults to just all zeros, and that initial bit set. That would handle that nicely, I think. Yeah. Yeah, if the pair exists, if either pair for each pair, check if it exists. If it does, recurse and update the max bit set with what you get on that recursion. And before you recurse, you want to give the bit set to that recursion, give it the updated, where that target bit is flipped. Yeah. Okay, that makes sense. Interesting. The position is flipped to on. That's how you handle the recursive case where you're given two values in the range. you would just ignore the ones that have just that return a single range value. I think in that case then you only need a you only need another routine in the beginning. It's sort of another while loop where you just have to split your range into two pieces somewhere. So you can have a recursive subroutine that takes two different ranges, right? And again, we're calling splitting. It's really sorting, sorting within a certain section of the array, doing an in-place sort, and checking to see sort of what the size of the results are. I guess if it was we'll just say the size. Yeah, we'll just say the we're sort of sorting and splitting at the same time because we're sorting on a 0 or a 1. So if we're sorting sort of decreasing, then all the values that have the 1 are going to go to the left, and all the values that have a 0 are going to go to the right. And we're going to do all of it sort of in place and all about it as stably as we can, using a stable sort. So super interesting. So I think the only issue is the first sort, to get the first initial most significant bit, the first time that we see a split. That's kind of a repeat of the same routine. It's just a while loop until you keep increasing the position and sorting on that range until you actually have something on the left side, something on the right side. And then from there you would recurse on the routine that has two ranges. You actually could probably modify the routine that has two ranges to kind of be somewhat degenerate in that, or not degenerate, but like it can handle only one range as well. So like if the second range you give it is a degenerate range that has no empty range, then it would just basically process that range as if it doesn't exist, effectively skip over that range. So then what would happen? You would never have these pairs though, so you would never really. Yeah, actually no, that would be fine. That you would never have this pair, right? Because you don't have another range to operate through. So then you would recurse on. You would split this range into two ranges. Call the recursion there. I'm sorry, what would it do? It would. You wouldn't have. All these pairs would fail, right? You would have, these pairs would fail, right? You would sort of you're considering this bit position. You would just thinking. I'm not sure if it's better to just keep this logic separate. It probably is. I think it's simpler to just keep it separate. But you probably could write this in a way where it's not separate, and it's sort of like could handle the degenerate case where one or both of the ranges are empty. I think you actually do need to handle that case because at some point they are going to be empty. The ranges that you're working on, you're operating on. Not really. It actually doesn't matter. The edge case that Well, yeah, there's two edge cases, and there's two, not edge cases, but two base cases, sort of, where the recursion stops. One is when you have processed all of the bits that you're interested in, the 32 bits. The other one is when the actually the range of numbers disappears, right? There's no range to operate on there. Yeah, I think I mentioned that before. You just skip it, right? If you just don't have a range, like if you're missing this one, or then you don't operate there, or if you're missing this one, then you don't operate there. But actually, you wouldn't operate on either of them in the case that this range is totally empty. The second range is totally empty. What would happen is you wouldn't operate on either one, and you go to the next bit. You'd have these two ranges though. But I think it would always give you. I think it wouldn't work. Yeah, because you would never. Yeah, because what you default back to is assuming that the second bit didn't matter, but you still have something in these two ranges. So yeah, no, so you do need something to give you like two non-empty initial ranges. Yeah, that base assumption won't hold. It'll get too wonky, too funky. That's different from what he did here. I think what I'm describing. Okay. What he's doing here is very different from what I'm thinking about doing. I think they're totally different. I think I don't really fully understand what he's doing here. Excuse me. Excuse me. Huh. I don't really know what's going on here. I don't know. Interesting. No idea. Don't get it at all. Could tell you what I'm thinking about doing and try to write that. It's confusing. Probably not the best. Definitely not the same as this though. I don't know, man. Not a clue. Not a clue. I don't know what is going on here. I'm totally confused. Alright, let me try to code what I was just describing, because I really need to use the bathroom. Let me do this. Let me save this as the... Let me just save this somewhere, one that I have originally. I think what I had the first time is the best, because it's just really concise. It's efficient, it's concise, it's simple to code, simple to understand. It's linear. I think this is the best approach, in my opinion. This is like the simplest way to thing to understand. What I'm about to put together is a little more complicated and kind of hard to understand and hard to explain, I think. Yeah. Okay, hold on. Where do I save it, those, is the question. Oh, I haven't. Oh, interesting. Okay. Let's go with maximum XOR of two numbers. All right, I think I've been using two different machines. I forgot about that. Using two different machines in order to when I was solving these problems. So I think that's why I feel like I'm looking at like where would I normally save this, and because I'm using two different machines, I save this in a different spot on a different machine. So I was kind of confused. Alrighty, yeah, so that's that one. The new one that I'm looking to write, we're gonna have a subroutine. We'll call it just recursion, I guess. Excuse me. And this is actually going to take we could use indices to keep it simple, I think. That would be better. So int left begin, or L begin, L end, right begin, right end, and oh, S and E must be start and end, right? That must be what that is. RS, yeah, start and end. And we'll do begin and end, then we'll do LB and LE, RB and RE. And I think that's fine. These also could be pointers too, but we'll come back to that in a moment, I guess. Oh, and then bits. Bits and position. So, so we want to say, so assume, and we also have a F is the recursive portion. We're going to use an N element too, I think. Algorithm, right? That's what we want. So we're going to say call it ret. It's going to start off at bits. Return ret. Going to have a while loop, and it's going to be position and 0. We'll do something like this. We'll just do bool, or no, yeah, we'll do it this way. So it's definitely a bit confusing. So I want to split on the left side and split on the right side, which is going to be do we not get first, last, nth? Okay, on this comparator. Can't actually just use the nth element the way that I would like to, because it doesn't give you the pivot that we're looking for. We actually want to know. Oh, that's awkward. We want to partition based off of this bit, but we also want to know where our partition ultimately finished, right? In other words, we want to know, like, oh no, gulp. This actually might be what we want. Interesting though. It's not quite what we're after. I think we do need to write our own custom. It's kind of annoying. Our own custom partition, sort of a three-way partition. It's not really a three-way partition though. It's just a two-way partition. I don't remember how to do the three-way partition. I don't think I'm ever gonna commit that to memory. The three-way partition. It's like I always forget how that works. But yeah, basically a degenerate three-way partition is what we're going to need to write, because we need to know where we partitioned, right? It's not enough just to partition, because I mean, I guess it doesn't matter that much. The other thing we can do is just write the we can run the nth element partition and then just do another quick sort of left to right check to find where the elements move from one to the other. But the problem with that is that uses an extra pass, which is unnecessary. So I guess we do need to do something very similar to what they're doing here. It's kind of annoying. Kind of annoying. Okay. Sure. Maybe I'll write a subroutine to do that as well. Just a partition routine. Don't really want to do that, but I guess that's just what we should do. Okay. The start is the start, there's an end, and then there's a bit position that we're going to use to partition. And what we want to do is, we're not going to bother trying to figure out whether or not we're in a degenerate case or not. But we do want to return the split position. And that's going to be where, I guess we'll just say where the first 0 appears, right? The first bit for the 0. So if we look at the three-way partition, we can use that as a guide. I don't want to just copy paste what the other Leetcode solution has. Whoa. That's not what I'm looking for. Strongly MP complete. Oh, that's a much harder problem than we're looking for. Excuse me. Not the three partition problem, but the three-way partition problem. Or Dutch partition, I think. It's like Dutch partition. Dutch people. Nice. Partition algorithm. Just don't remember how it's done. There's a good one somewhere on Wiki, which I can't remember how it's done, where it is. We'll just go with this, probably. probably find it somewhere around here. I don't know. Whatever that is. No, not subset sum. No, these are different. This is way more. It's not what I'm trying to do. No, this is way more than I need for what I'm trying to do. There's a really simple algorithm out there that I forget what it's called. Just forget the name. Oops. Not number partitioning. It's just the sorting, like three-way sort. It's like a super. Where is this? Patient sorting. Interesting. Length of the longest increasing subsequence in a given array. Oops. Okay. Bead sort, gravity sort. Where is it, man? I can't find it. Gonna lose my marbles. There's Really gotta use the bathroom too. I guess we'll just hold it. Tim sort. Android, Java, and Python. Stooge sort. Excuse me. Pancake sorting. Oh boy. It's not here. Can't believe it. Can't believe it. Tournament sort. It's gonna take a while to find this, huh? I was hoping it was somewhere in this article. It's not. Flag sort, I don't know. Is this the one? Yeah. The Dutch national flag problem. American flag sort. Is that the one? Variant of radic sort. Items in the buckets. Yeah. Stripes. Confusing or unclear. Okay. So yeah. This is what I'm looking for. A variation of radic sort called the American flag sort. Found it. took a while. We got there. Oh, great. That's great. Anyway, yeah. 2 stripes. American flag sort with 2 stripes. That's what we're looking for. Radic, form of radic sort. What is the general algorithm? First pass, compute counts, 0s, radix for object x and array, counts digits +1, bucket offsets, swap objects into place, bucket starting at this offset, for each bucket, American flag sort, bucket radix, swap. Neat. Neat. You could do for any number that has like bits, I guess, or any number. Yeah, if you have, you could use American flag sort for all of most efficient with the radix to the power of 2 bit shifting operation used instead of exponentiation. Balance the sorting by character by character. I really gotta use the bathroom. I think I'm just gonna go. Alright, I'm just gonna say be right back. Wow, I've been at this for 5 hours, no kidding. Whoa. Whoa. Yeah, I'll be back. Just give me a few minutes. So we'll keep going. Yeah. We have, right, American flags. Yeah, so I guess radix sort, I don't know, radix sort is, it's pretty much the same thing. It's just the variation of radix sort, really, ultimately. Yeah. Which is pretty much what we're looking for. We're looking for a version of this, but with only 2 items. Not a 3-way partition, but a we only want two buckets though. So I is 0. Wouldn't even have a j. K is size of a minus 1. J is less than or equal to k, so the I is less than or equal to k. Swap if we're less than a of j is less than mid. Basically we want everything on the left side to be a 1 and everything on the right to be a 0. So if a of k is a 0 and if I is a 1, then we would move forward. A of k is a 0. I think we could do it that way. I think we could write our own. I think we'd be okay. Let's try to write our own, see what it looks like. So you start and end, so the I will start at start, and j will be end. And if we say if nums of I is equal to, we have a for loop, right? So it's really just a while loop. While I is less than j, I mean, really could just do a for loop instead of a while loop, but that's fine. So I is less than j. If nums of I is 0, then I guess there's 4 cases, right? Decrement j. Do something like this, and then increment I, decrement j. And in the 4th case, they're both equal to 1, then you don't want to, you can increment I think. Yeah. I think this is what you want to do, something like this. And then you want to return something important. It's actually really A and should be A and B each time. Okay. Wow. Okay. Okay. Kind of involved. Some alarms on my phone are gonna start going off. Wow, I spent a lot of time on this. I mean, I don't know what to say. I guess maybe it's too much time. Probably. So these four cases are all different, right? In both of these cases, you're gonna modify this, but you're also going to swap in this case. In this case, you're going to decrement j. In this case, you increment I. All three of these cases, you increment I. All three of these cases, you can decrement j. Only in this case, though, do you swap the two. I don't know, man. I think it's easier to just go through all four cases. Like, it's... yeah. Mm-hmm. Yeah, it's probably easier to just do it this way. All right, anyway, so we want to return now. What happens when you I is less than j? So I is going to be moving past j. I initially is at the start, j is at the end. If they're all ones, then I is going to push all the way to the edge. I think I is going to be the first position, the first 0. So you want to return I. It's always going to be the position of the first 0. And if they're all zeros, then j comes all the way down to -1. If they're all ones, then I goes all the way at the end. Yeah, so you just return I. And I may or may not be off the edge. Sure, that's fine. So that's our partition. Great. So what I've been saying is we want to partition I gotta get back to my friend. Let me come back to him on that. Only because probably would want to only because I probably want to focus on that, and I also want to focus on what I'm doing now. And so I want to focus on that thing and also focus on this, finish this thing. I don't want to, I kind of don't want to split this into multiple pieces. I kind of want to finish what I started with this, so to speak. I do appreciate how long this is taking though. Like, it took me like an hour to solve the problem at a reasonable, kind of clip. Like a reasonably efficient solution, and then now I'm trying to like really trying to optimize that solution. And it's taking me like, I don't know how many hours we're at this now. 5 hours. Oh boy. Oh boy. Wow. Okay. Okay. So, right. So while position is greater than 0, we're going to partition on the left beginning and the left end using this, position. Say split A and then split B. So left beginning, right ending. Okay. So we have these bits that we're given. We're going to split on the left side, split on the right side, and basically if split A is greater than or equal to the left side, or split end split A, so it's pretty much, if we didn't break anything, right, this means that there was a split to be had there. Then we're going to recurse on the split positions, which is, we'll come back to that. So we'll say just call x equals 0. And then we're going to say, if that's true, then we're going to say x equals standard max of x in this recursion. And do the same thing on the other side for b. So the right beginning, we'll split b, and the right ending on split b, and we'll do x equals, and then we do ret equals standard max of ret and x. Okay. Yes. Okay, fair enough. And we would say couple of things. There are a few things to consider here. A few different like manipulations, I guess. F, we want the left beginning. So we said I is going to point to the first 0, so I minus 1. So it's actually going to be greater than the beginning of this. And it's when the first 0 appears. Yeah, it's going to be, yeah, like this. Right, because the first 0 appears at, if the first 0 appears at the very beginning, that's a problem. So it's actually going to be less than, it's got to be to the right of the beginning. Yeah, okay. So LB and I minus 1, and I to RB, or to LE, yeah. And the bits and the position and F. So this is the recursion that we're going to perform. Very similar to this one, which is, it's almost the same thing. Not I though, it's split A. Similarly for split B. And this is going to be the right side, the right beginning, and right end. Okay. Okay. So now the tricky part here is this is wrong. What we just did. This is actually just wrong. Yes, this is incorrect. So the recursion is going to be on AA and BB, which is we don't actually know which ones we have here. Which ones are missing or not missing. So this is incorrect. This is just wrong. Close, but not quite right. Okay. It actually matters a lot which cases we're dealing with here. Huh. So basically, we want to know if if 1, 1 exists, that means that split A is greater than the left side, right? Yeah, split A is greater than the left side, and we also want split B to be less than the right side, the right ending. So we know we have 1, 1 on the left side if split A is not 0, or is larger than the left beginning, and we know we have 0, 0 on the right side if we know that split B is less than the right ending, which is a little confusing. It's less than or equal to the right ending. Yeah, that's pretty interesting. Okay. So, okay. Oh boy. That's great. Oops. Not what I meant to do. Yeah, I don't think I would code this up in a coding interview. Code it this way, definitely not. So now we have left B to split B minus 1. This is all the one. These are all the ones, and then you have split. Excuse me, it's split A, rather, and now split B to the end is the those are all the 0, 0s. Gotcha. There you go. That's fun. Okay. And you do a similar kind of a thing over here, basically the inverse. So this is going to look like yeah, pretty much just flip these. So now you have in order to have 1, 0, you need to have the split, well actually it's really split A. Yeah, you do split A is less than or equal to left end, and then split B has got to be greater than right beginning. Yeah. Yeah, so that means that if split A is less than the left end, less than or equal to, that means there's at least a 0. So you have 1, 0, and then this other side means you have 0, 1, 0, 1, which is right. The right side starts with 0. Yeah, it starts with zeros, and there's at least a 1. So, right, it's not all zeros if it's split B. Yeah, it's it's great. Perfect. And that means the left beginning here, it's not left beginning anymore. It's actually going to be split A minus 1 to the left end. And then this is, oh no, excuse me. Yeah, I think that is, yeah. And, no, yeah. It's actually just split A. Split A to the left end, and this is split B minus 1 to the right end. No, that's not right either. It's right beginning to split B minus 1. So very confusing. But yeah, basically these are, like I said, these are just inverted. So LB to split A minus 1, then this is just split A to LE, and then the other side is split B to RE. This should be RB to split B minus 1, right? And these bits positions. So this position increases by 1. So this gets bit shift to the right, less significant bit now. Is a less significant bit now, bit shifted to the right 1. And these bits, you would OR with the position. Let's call this V. Oh. Put this all in one line. So yeah, you know that you can place a bit there now in that position. So you recurse on the next sort of position over. And now you can just take this maximum of X and V. Do the same thing here. I have this uneasy feeling like this is not going to be more efficient than what I wrote before. Somehow this is just not, it just doesn't seem like it's going to be that much more efficient than what I did before. I don't know why I get that feeling. I think they're still technically linear. It's just, I don't know. Something just seems like this is going to be a little more heavier in terms of a little more exertion to do it this way. Yeah, there we go. So, yeah. Now the deal is, you could partition both of these, and they both come up empty, and so none of this happens. In which case, you go to the next position. So I want to say, like, if either of these are, I don't know, I'm not exactly sure how to do this. So you don't need to keep recursing, like you don't need to keep iterating so I want to do something like this. So Boolean check equals, say, false, and here we'll say the check equals true. Here we'll say the check equals true. And then we say if check, then break. That's pretty much, yeah, then we just do red equals. Yeah. We don't need to Otherwise, we update our position and keep going. So what the idea is that if both partitions fail, then we would skip this bit in our bits set. We wouldn't set it to a 1. It would be set to a 0. And at the end of all of this, we're going to return this ret value. So this is that recursion I was describing before. It's kind of hard to describe it, and then the code is about as confusing and wonky as the description was. So this is this is great. This is definitely not better than well, this actually might be faster only because we don't have a set that we're dumping things into. I think it will be better. Yeah, give me 1 second here. This has been an interesting question so far, though. I'm grateful for this. So now we have an initial loop as well, where we want to partition, find the first significant bit where a partition exists, basically. Partitions subrange based off bit position. Be a single bit. Set to 1. Bits set to 0. In descending order. Really sorts a subrange. Sorts 2 subranges into smaller subranges recursively, and returns the updates and determines and updates depending on whether smaller subranges, depending on which smaller subranges exist. Yeah, something like that. Sorts 2 subranges into 2 smaller subranges recursively and updates a given bit set, depending on which smaller subranges exist. Yeah. Neither subrange exists, the bit used to split into or partition or to sort determine and sort will be updated. Okay, so now we want to say, finally, find the most significant bit that will exist maximum XOR of the values. So you want to find that first, and sort the numbers into two subranges based around that bit. Yeah. I'm calling it a partition, but it's sorting. All right, so to do this, we would say int position equals, excuse me, it's really one bit shift to the left 30 times while, so boolean check equals false or true. I'll check. We're going to say partition of partition. Also, this is not recursive, so we don't need to do that. Partition of 0 to nums.size -1 of position int x, say if x is less than 0, or, well, say x is greater than or equal to 0, or x is, hold on, how do we do this? Yeah, if x is less than 0, or x is greater than or equal to nums.size, then we failed. Check is true. Otherwise, so if the partition worked, I think x has to be greater than 0, right? Yeah, x is the first 0, so there's at least 1, 1, and x is less than nums.size, less than or equal to, or yeah, less than or equal to num size. That means that it's there's at least 1, 0 if it's less than the num size. Then check equals false. And we can sort of continue. Otherwise, we got to update our position. Just shift that to the right 1. And our initial bit set is going to be that bit, I think. So we'll call this recursion here, recurse, on so check and position greater than 0. So if position is 0, turn 0, right? That means that there were no bits to start with. Otherwise, we're going to recurse on this partition, which is going to be the left side is going to be 0, the left end is going to be x minus 1, the right beginning is x, the right end is nums.size -1, and that's 1, 2, 3, 4 bits position and f. Bits position and f is recurse, and bits is going to be that position. That's the most significant bit is going to be set, and position bit shift to the right 1 is going to be the first position, and then sort of the next position, first position to be interested in. Something like this is what we're looking for. See if that compiles. Swap. Where's swap from? I think it's utility. Really? Oh, I see. Okay. We may not actually need utility in there. I don't think we do. What is this? Cannot be used before it is defined. Deduced return type. Excuse me. That should be fine. Declare it here. Could just figure out what the, we know what the return type is. Time limit exceeded. At least it compiles. Shouldn't TLE on 6 elements. That shouldn't happen. We know this doesn't. Oh, well, the base cases I think are the problem, right? Yeah. So. Interesting. Actually, this is the base case. This position greater than 0. That's pretty much it. What happened? Where did we TLE? Okay. I don't know. Interesting. You're kidding, really? How? What? That can't be true. Well, if we're here, both of these, if either of these cases is going to eventually cause us to exit. What happened here? What happened here? I never reached this line, so we get stuck in this loop. But how do you figure that? how do we do here? Check 1 all the way down to 116. Now, for some reason, it just doesn't print out anything more there. What is going on? What? Hmm? Hmm? I mean, what? It just times out here? Is that? It just gives up after this point? Is that what's happening? Hello? Okay. Why though? Huh. What is going on? What is going on here? I don't understand. Oh yeah, okay. Oh, look at that. What? TLE's here, but what? I am so confused. Check 1, position 0. Okay, so the position does get down to 0. So this... Does this ever get called? That's something I'm very confused about here. No. So I'm completely confused because this never gets called, but this is an if-else, so this has got to just be calling this a bunch of times. Where is this timing out? Like how? Excuse me. How is this happening? Check 1, position 2. Because there's nothing gets printed after this, so it couldn't be in this loop because it would be printing this, wouldn't it? So that's just completely confusing. I don't know what is going on. I don't know what is happening. All I'm trying to find out with this routine is the first time that a bit is relevant to the integers that we're working with. So meaning there is at least 2 different numbers such that one number has a 0 in that bit position, the other one number has a 1 in that bit position, right? Because all the other bit positions, they're all just 1s or all 0s, then we don't care about that bit, right? That XOR will always exit, that bit will always be gone, a 0 in the so confused. See, that's the thing, it's TLEs, but we never reach this position. We never reach this, so we TLE somewhere in here, it seems. what to do. Or maybe, oh, maybe it's this one that TLEs. Was not expecting there to be issues with this routine. This one seems solid though. I don't know how that could be. Ah, that's why. Get to check A, and we get stuck here with TLE on this partition. So somehow this partition, I is less than J. Why does that get stuck? Check 1, position 2, 1, 2, 3. So position is 2 here. A is all these things. I think that might be the issue, is that these aren't zeros or ones. This is yeah, if you convert these to booleans, so we would do instead of 0 and 1, you'd actually do position. That might be why. That's definitely a little bit confusing. Maybe that's the problem. Okay, there we go. That's better. Definitely was not expecting that. Okay. But I can see why I wasn't expecting that. I can see why I wasn't expecting that now. Okay. So 1, 2, 3, expected 3, output 0. Really? Okay. Oops. 1, 2, and 3 looks like the following. Actually, you don't even need, it's just 2 bits, right? 1, 2, and 3. If you XOR any of these, yeah, actually these two will give you 3. So, okay. So we find our first bit is this one, right? And we set that to true, position. And that should be 2. Oh, no kidding. Really? Well, that's odd. What? 1, 0, 0, or 0, 0. And this is never reached. Oh, okay. Let's see. That's also my mistake. Oh, there we go. Sweet. You know, it's funny. I wrote this intentionally so that the less than symbol would be in the right spot. Actually, I think x has got to be less than or greater than or equal to 0, because that means no, it's got to be greater than 0. Here. X is where the zeros begin, so it needs to be, yeah, okay, no, that's fine. I don't think these are right though. Nope, that's fine. No, you're right. It's okay. This is inclusive, the endpoints. That's something to remember. Right, so actually we're correct for this case, but what about the other cases? Just because we got lucky on one doesn't mean we got, we're right. Yeah, okay, good. It's good that we're wrong. I was expecting that. That would be suspicious if we were correct. We had a bunch of other test cases before, but we'll take a look at those shortly. All right, so we have one failing test case already, so why would that be? I guess is a question. 326 and 328. Where did we get 26 from? How did that happen? How did that happen? Two and 16. Wait, what? Oh. Get rid of that now. Oh, my body. Oh, I gotta stretch. Okay. 26, 28, 16. So, okay, I guess that makes sense. So what are these numbers? What do we expect to happen here? Okay. What do we say? We said, yeah, this one. Okay, so that's a whole bunch of zeros, a 1, 1. 32 is only 5 bits. So, there we go. 10 is 4th bit, these 2 bits. Alright, that should be 10. 5, alright, 0, 1, yeah, 2, 1, 2, 4, 8, yeah. 5 should be 2, 4, alright, like so. 25 should be 16 and 9, so 16, 9 would be 8, and then a 1. Alright, that should be, yeah, 25, 2, and 8, which is just 3 ones. Oh, no, excuse me. This 1. Okay. So what happened initially is we would get this first bit. So position would be initially 16. This is what we see, right? And then we would operate, we would split this into 1, 2, 3, 4, 5, and a 1. No, so this 1 would go all the way to the top, right? So this 25 would go up here. So 25, and then the others, right? And then what you would do is $25 and the others, you would split this range into two pieces, which we did, and run that recursion. So 25 is sort of one section, and the other section is the rest of it, right? So we would expect to see basically x is 1, right? Let's see that. Yeah, okay. Then we do our routine now. We have two ranges that we get, and now we're going to split those into sub-ranges. So now these two sub-ranges, this one, we're splitting on the second one. So now we would have 25 up here, and these two ranges probably would be these two numbers, right? 10 and 8. Something like that, and the other ones would be 5, 2, and 3 somewhere. Something like this. Yeah, this is kind of like a radix sort that's sort of on the bits, sort of we're kind of, yeah, kind of performing a radix sort on each part. 25, 10, and 8, and what's interesting is also the 25, 10, and 8 get split into two pieces, right? This is 1, 1, this is 1, 0, 1, 0. And, oh no, excuse me. This is sort of split into two pieces. This is 0, 1, and this is 0, 0. Right. So the recursion we do now, right, 0, 1, and 0, 0. We only have 1, 1, 1. We don't have 1, 0. So I think one of these recursions doesn't even happen, right? I think it's only this recursion that we care about. That's kind of what we were talking about before. This 1, 1, and 0, 0. This is the 1, 0, and 0, 1 doesn't even happen. So this partition, when this happens, when you partition on A, so this is 0 and this is x is 1. No, x is 1. 0, 0, right? This partition on 0, 0, this just returns immediately because they're equal to each other. I'm not sure what the meaning of that is, actually. This is a little confusing because if there's only one element in that range, we don't necessarily know what the value of that is, if it's a 0 or if it's a 1. Which is definitely a little bit confusing. Yeah. We probably want to think about that. We always want I to be pointing to the first 0. So we'll do it like this. Edge case. S equals E. And we'll say if S equals E, then we'll say if nums of S and position equals position, then return S plus 1. Otherwise, return S. Right. So we always want to return the first 0. Yeah. Okay, a little bit better, but not much. So this is a 0, we'll return S. That'll be the first 0. Yeah. The question is, what's happening that this is not? So do we get this 25 and 523? That's a good question. Have a test 1 and a test 2. Give those a shot. So yeah, we get test 1 3 times. We never see a test 2. Okay. So what do we do here? Oh boy. Yeah, we want the test 1 because that'll give us 25, right? And test 2 shouldn't even exist. Yeah, so we just skip those altogether. Then we have 25, 5, 2, and 3. We would check the next bit. We said 25 looks like this. 110011 or 11001. 5 is 00101 and 2 is 00010 and 3 is 00011. Right. So yeah, so we know that any pair of these will give us these 2 bits. Now we want to get a pair, or rather 25 paired with any of these will give us these 2 bits. Now we want to pair 25 with this 3rd bit, this next one. So we would say probably we have the first bit we kind of drop off. So we have 1 0 for 25, and then we have which is 25. We don't have 1 1, that's gone, right? We have 0 1 is 5, and 0 0 is 2 and 3. And so we actually lose these because there's no that doesn't exist. We gain this one, right? So we would skip. So actually we shouldn't do test 1 again. That's actually, I think, incorrect. It should be test 2 the second time. Why did we get? We got test 1 again because, oh, this is arduous. Wow. Okay. Well, I mean, we're doing it. Let's finish what we started here. Let's do that. So Test 1. It makes sense the first time we would do test 1. The second time, though, when we recurse, split a minus 1 is left beginning. Yeah, this should be just pointing at 25, right? This basically should be this should be right, we expect that 1, and split b is 3 though. That's interesting. So 3 to the end of r, which is, don't necessarily know. Yeah, 0, 1, 2, 3. It should be 3, right? That's correct. So the first time we call that should be 3 to the end. But the second time, the next time we call this, we should see split A should actually not be 1, 1. It should actually be over the edge. Split A is oh, that's interesting. I'm actually not sure now. This is really confusing. We said we want that return partition point to be where the 0 is, which is going to be to the right. If it's a 1, 1, it'll be to the right. If it's a 0, it should be right on that spot. And actually, should be 0, I think. This should fail the second time around. This should actually. What do we get? What do we get? 1, 3, 1 again. You shouldn't get 1 again because the reason you shouldn't get 1 again is because of this should be should be 0. This pretty much should just consist of 25. Right, 0, 0. But the position changed, so that's the thing. This position's bit shifted. So now, when I look at 25, it's not 16 anymore, it should be 8. And when you look at 25 with 8, oh, it is a 1. No, it should be 0 though, no? This should be an 8. And then, yeah, and then this should be an 8 the first time. The second time, there should be 4, which should be a 0, right? This should be a 0, which means that this should be false. I mean, this should return 0, not 1. 825, 425. Yeah, that's what I'm saying. L and E, yeah. Huh? Okay. What does this look like? Ret 1. That makes sense. So that doesn't make sense. This should be 0. 25 and 1 and 4. 8, 16, 8, 4. No. Wrong. It's incorrect. How do you build 25? It's 25 divided by 2 equals 12, remainder 1. 12 divided by 2 is 6, remainder 0. Yeah, I have that right. Fine. It's 110011. This is incorrect right here. Oh, is S 1? Is that the issue? Or is S? No, S is 0. I'm so confused. S is 0. Numbers of 0 is 25. Testing position. This position is 4. 4 and 25 is not 4. Hello? Oops. Just gonna run over a line here. What is going on? Oh, you're kidding. What? Uh-oh. Now, how did that happen? Excuse me? That makes sense. That should be an 8. But this is equal to a 1. How does that be? How's that a 1? You what? You what? That's an 8. Excuse me, this is a 0. This is a 4. This should be a 0. What is going on? What is going on? There we go. Okay. So that's confusing. I think what happened is that this equality came first. I think it's a order of operations. So if you see an AND, you're going to want to a bitwise and, you're going to want to encapsulate that with a parentheses. There we go, now we're correct too. Okay. Wow. Talk about an unusual error. I think I've seen that before too. Yeah, it's an order of operations issue. Okay. No kidding. Alrighty. Okay. Alright. Let's try some larger test cases now. One, 0, 100. End up with an E in there. This is interesting. I'm trying to incorporate zeros and okay. Alright, let's see how we do here. Let's see how we do here. Okay, this is promising. This is looking promising here. I guess we just go for it. I don't know. We probably have a mistake somewhere, an error somewhere. Yeah, certainly. Just there's a lot of test cases to go through with this. I think we spent kind of a lot of time already. The reason is there are like a few different kind of edge cases. I'm not really sure exactly how to reach them. I would need to go through like a lot of different possibilities cases. It has to do with like where things are being split on the, I think it's on the edges. So yeah, we could somewhat do this by hand, I think. Oh man. Wow. So, 92, right? Okay, 92, sure. Can do that. We'll do it like so. So we have 0, 0. Right. 1, 2, 3. 4, 5. 2 divided by 2 is 1. Excuse me. And then 1 divided by 2 is 0. And so now we have 1, 0, 1, 1, 1, 0, 0. This should be 92, we said? 1, 2, 4, 8, 16, 32, 64. Give us 64 plus 16 plus 8 plus 4, 92. Okay, great. Alright, so this is one of the numbers we have. 91 looks very similar. I want to say like there's probably a few different things here. So do we have at least a number, some other bit? Yeah, we do have some other number where that's zero, a number less than 64, right? So there is somewhere in here a number less than 64. So we would split on all the numbers that are greater than 64 and the numbers that are less than 64. That's the first split. And that would give you 92, 91. We'll just circle them and highlight, underline them in red. So greater than 64, 64, 64, yeah. So we would have 92, 91. Doesn't really matter. I could do 70, 83. Already said 91. 80, 92 we have at the top. 66 and 70. And everything else is beneath these two. Which is like, or just right on the side, 14, 53, 49, 36, 51. Okay. All right. And these numbers, I'm going to split this into zeros and ones, right? Or yeah, we want to split this again on the next bit. So everything greater than or equal to 96, which is nothing. So this is all in one giant chunk of 10. And this bottom one is a 0 and or any of them greater than 32. I think they're all, yeah, this is 0, 0. These are all greater than 32. These are all 0, 1. So this is the first iteration. This should be test 2, we'll say. So let's check to see what we get. I have a test 1 and test 2 again to see what we ended up with. More likely than not, the logic is fine. It's just there's some like off by 1 error somewhere, just something silly that I missed here. So test 2 should be the first one. Makes sense. Good. And you wouldn't even bother with this 14, so you just kind of lose that 14. Now the next bit that we consider, we would want to split these into pieces again. So this is the next bit is 32. Everything that has 32 set. So if you subtract 64 from all of these, those are greater than 32. Which none of these have that bit set. Or no, excuse me. Yeah. So we get the first bit we're gonna take with certainty. The second bit, we want to recurse on, and we take that as well with certainty. So we're at 96. It's the third bit, which is 16. So is 16 set for any of these? So we subtract 64 from any of these. Do we have 16 in there? Are they greater than 16? 64 plus 16. 70, 80? 64 plus 16 is 80. So everything greater than 80. So these are all greater than 80. No. Greater than or equal to 80. Right? So these are all 1, 0, 1. And then these are 1, 0, 0, right? Okay. So this is 0, 1, 0, 0. And on the other side is we subtract 32 from these, and we want to see if it's greater than or equal to 16. So that means 32 plus 16 is 48. So everything that's greater than 48 are these are 0, 1, 1, 0, 1, 1, and this is 0, 1, 0. Right? And so what we're pairing off now is 0, 1, 1, I want to say, with 1, 0, 0, which we have a few. And also the other way around, 0, 1, 0 with 1, 0, 1. So here's a case where both recursions are going to happen, right? That's going to split us up into two different recursions, which is 0, 1, 1, 0, 1 is 92, 91, 1, 0, 1, 92, 91, 83, 80. 1, 0, 1, right? 92, 91, 83, 80. And the other one is 70, 66, and 70 again. Okay. And by the way, these are all going to end up next to each other, consecutive, because they're being sorted, so they're all going to be consecutive with each other. So, and then you also have, so this is 101 is the larger crowd here. This is the 100 crowd. Then you have 57, 53, 49 is the 011 crowd, and then 36 is 010. Okay. You have these two groups, right? So these will pair off, and these will pair off. Now, ultimately, I think so all of these will give us, all of these are going to give us the first 3 bits, which is 96 plus 16, 112, right? So all of these will give us at least 112 so far. Now, in each of these now obviously this is like the recursion part. We're dealing with 36, so we can kind of figure that one out quickly right now. So look at XOR. Let's get our programmer calculator. Let's use an XOR bitwise. Yeah, let's do that. So let's do 92 XOR 36. 92 XOR, no, excuse me, 91 XOR 91 XOR 36. Okay, that's the one we want. (91, 36). Ultimately, this is where the path we want to look at. That gives us 127. Somehow we missed that one. So that's going to be. That's actually not. That's pretty close to the top as far as like all the different sort of where we go in the tree. Basically, that's going to be a test 1. No, excuse me. Test 2. Test 1. 92, 91, 83, 80, and 36. Yeah, it's just a test 1, a test 2, test 1, and then while we're going through test 1, we'll say what's the next bit? There's 1, 2, 3, 4, 5, 6, 7 bits. So 1110. 7 bits. So we have this up to this point. And what we're going to do is test this next bit here. So this is, we said this is 1, 0, 1, and 0, 1, 0. So this, what is it, 64 plus 16 is 80. So 80, this will go to 0. So actually you can just write these out, I think. Um, 3, 11 is 8, 3, and 12 is 8 and 4. And then 36 is, I think 4 here. Looks like this. So when you XOR these, I think, yeah, 91 is the best, right? What happens though is we should check, we take this next bit and we say, so we split this into, yeah, 91, 92, and 83 and 80. Excuse me, and this split will just be 36 again. And the next test will be, and the next thing that'll happen is, I think you end up taking, it depends if there's zeros or ones. So this portion with 36, I think that's what the next step is. So this one and this one based off of this bit, right? So 36 is a 0. So then you end up with 92, 91, and 36 with these 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 0, 1, 1. And this is 0, 1, 0, 0, 1, 0, 0. And then you get the next bit here. 1, 2, 3, 4, the 5th bit. So these two are different. And this one is also different. So what happens here is, yeah, 92 and 91 are now on different spots because they differ by this 1 bit here, this 5th bit. So that 4th bit, you would ignore 83 and 80. Or you may or may not actually, yeah, you probably don't process 83 and 80. I think you just split into these two groups because 36 has a 0 there. And now 36 has a 1, and so now you're actually, this 92 and 91 becomes split again on this bit into 2 pieces. And 36 is a 1, and so we actually get paired off with 91. And then you'd have 91 and 36. And at that point, you should collect you actually don't need this check. I think. That saves us a whole bunch. Take that back. I think actually we did terminate early. I think we want that. I think we do want that. But in any case, we I think what will happen here at this point is once you get down to these two, should kind of go bit by bit. I think it'll set all of these to 1. So we're missing 2. So I'm wondering if this is, I mean, there's a lot of bits. This is 1, 2, 3, 4, 5. So -3. Should be 124. Like actually, all of these are set, right? It should be 127. Should be just the whole thing, all the way across. All the bits get set. We're missing 2 somehow. What is? Yeah, let's run this again. This is actually. We could check this. Which case is this? This is going to be a test 2, then a test 1. So 2, 1, 1, 2, 1, 1, 2. 2, 1, 1, 2 is the sequence. And how do we identify this here? So we'll put it in 2, and the split is going to be, or the left and the right, left beginning and left end is got to be 0 and 1, and 0 and 0. Yeah. And the right beginning, the right end. Mm-hmm. 2, 1, 1, 1, 2. Oh, it's not 0, 0. Actually, it's 36 is way off to the edge, right? Actually, it's the smallest number, I think. Almost the smallest. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 11 is 14. 10 would be 36. I don't see a 2 in there. I see a 3, yeah. I think 36 is the second smallest. I don't know why there's a 0, 0. So I don't know what I'm smelling in my hand. My hand sometimes has just like strange smells on it from time to time. I don't know why, where it comes from, what happens to my hands with this smell. I should go wash them. 4477. Let's do this. Nums of LB and nums of RB. Let's see what this looks like. 70, 92, 49. At some point there should be a 91. See, that's something's wrong. It's hard to tell. No, don't do that. Okay. What's going on, man? Maybe we should just print all of these on all of them. Print out this output. Get some idea what's happening. Okay, so test 2, 0, 6, 7, 11. Right beginning is 36, left beginning 70. So yeah, I mean we expect that, right? We have seven things. 6 minus 0 plus 1 is 7, 11. 7 things on the left side, 5 things on the right side. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5. Right, that's the first iteration. And then test 1 doesn't even exist, right? And then test 2, we do that. And we said we split into two pieces. So we do have a test 1 and a test 2. Test 1 should be 0, 1, 2, 3, 4, and a 1. No. So that's interesting. So the test 1 and the test 2 after this first iteration should actually put us we said it's just test 2, and it's going to be this chunk and that chunk, and then that's the initial, yeah, and then test 2. Then we're down to really the same thing again, but missing 14. So it should be 4 and what did we say that it was? How many was it? It was, yeah. Oh, wait, we lost 2 on this test 1. Confusing, but 0 to 6, 7 to 9. No. Oh, we do lose 2. Yeah, you're right. 53, 49, 57. Really should only lose 1, I think. That's super confusing. I don't know how to follow. I don't know how to trace through this tree. It's like the most confusing thing ever. It's recursive. It's like, what am I even looking at? I don't know. No, man. What do we expect to happen? What do you expect these numbers to be? 1, 2, 3, 4, 5, 6, 7, 5. Initially, yeah, it should be 5 and 7. Let's do it this way. Let's get rid of this. I don't know. Yeah, actually that's fine. Yeah, because I think it's too confusing to be doing it the other way. Alright, what does that look like? Alright, so initially we have total left side 7, total right side 5. Then we have trying to prune things down a little bit. There's 7 on the left and 3 on the right. Yeah, that seems right, I think. So no, I would expect actually 4. Not 3. How did that happen? We lost one. Who did we lose on the right side? Something like this. $36, $49, $51, $50. So we just lost 53 and 14, kind of out of nowhere. Right, so, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Left side values, it's kind of what we expect, right? Everything greater than 64. Right side value should be everything less than 64. Then now we have another split on 0, 6, and 7, 9. Now how does that happen? So we lose 2 elements. I don't think that's supposed to happen, right? We lost. Is there still everything greater than 64? This is supposed to split into 2 pieces, into things that are greater than 64 that have 32 set, and things that are greater than 64 that don't have 32 set. So that would be things greater than 96 and things less than 96, but also still everything greater than 64. Whereas this set is everything less than 64 but greater than 32, and vice versa, everything less than 32. Those are the 2 different sets that this splits into. But somehow we lose 53. Right, 53 is not greater than 64. It's between 32 and 64, so we should only lose 14. So there's some error here. Yeah, we processed this right side. Probably just some mistake on my part. The beginning, split A minus 1 left, and then this should be split B to the end. Split B minus 1. The right beginning, split B minus 1. This is split A, the left end. You don't subtract 1 when you're going to the end. happen? How do we lose 53? What happened there? This is testing 2, right? And this is, we partitioned the left side and the right side. The left side didn't change at all, right? So split A, basically, everything is all zeros, I think. So split A is just left beginning, right? So that doesn't change. Split B, on the other hand, we should have 1 and 0, and so everything except 14 has a 1. So split B minus 1 to the end, or no, so the beginning to split B minus 1. Split B should be on wherever 14 was. Could show what this partition looks like, I guess. How do we call this one here? What is this? 10. Sure. That would be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That is wrong. That is incorrect. How did that happen? What do you mean? Position is... that's just wrong. Gotta be kidding me. You have got to be kidding me. How did that happen? 36, 49, 51, 53, and 14. And we're looking at this first position is 64, this is 32. 32, right? Everything is split nicely. Position is 32. Now we split on 32. So I split on the things that have 32 and the things that don't have 32. So everything except 14 has 32 set. Like, we know that. So what does that look like? Position is 32. These aren't equal. We ignore this. Start at what was this? 0, 1, 2, 3, 4, 5, 6. So start at 7, 8, 9, 10, 11. 7 to 11. I think it's supposed to be I is less than or equal to J. I think that's the problem here. There we go. Okay. That is fantastic. That is really frustrating. Of course. Of course. Wow. Yeah. I got this wrong too because of that. You gotta be kidding me. See, we could Yeah, I'll just go for it. Whatever. I don't know what's gonna happen here. TLEs. Okay. It's probably just from the debug output. I'm definitely annoyed that that happened. Certainly irritated. Gotta be kidding me. Must be joking. Oh, okay. I mean, you know, got 97%. Ho! Sweet victory. There we go. All right. Oh man. Oh, there we go. 36 milliseconds. Getting closer. Inching closer. Yeah, okay. It's definitely a lot faster. Did not reach 99.5% though. Got almost 99%. Got 98 points. Oh, there we go. 28 milliseconds. Be 99%. All right. All right. One more time. One more time. There we go. Rolling for the big money here. Rolling those dice. Let's keep trying. We're pretty close. We're 98%. We're, you know, I think what was 28 milliseconds was I think 99, almost 99. I forgot what 28 was. 60. We're okay, so we're above 95%. That's pretty good. I think above a 98 as well. Also my nose. Gotta stop touching it. 98. We're almost 99. We're so close to 99. I think we were 99.25, something like that. We're so close. We're so close. We have to submit it so many times to get. Yeah, 99%. All right, we got over 99%. I think with 28 was pretty high. Did we get 28? Or was that just my imagination? 32. All right, we got over 99%. That's pretty close. That's pretty good. Did I just think we got 28? Did we not actually get 28? We did get 28. Yeah, what's that? Yeah, 99%. Oh man, there's just a few solutions that are a little bit faster. 20 milliseconds? 28 milliseconds? 16? Oh man, dude, somebody's got 12 milliseconds. I don't think our solution is 12 milliseconds. It's pretty close though. Wow, 12. 12 is fast. 28, yeah, 99.37. 12 is fast. 12 is fast. I guess you'd have to optimize this code even more somehow. There's probably stuff we could do to make this even faster. But that's pretty crazy. I actually think I know what to do to make this even faster. So yeah, alright, we did it. That took forever. That took so much time. Probably would never do that unless like we really needed to have things be really, really fast, extremely fast. Wow. I don't even know what to say. That was a lot of time we spent on that. Probably not worth it to spend all that time. Probably not. I don't even know what to say. I don't even know what to think. Just that's it's one way of doing it. That is one way of doing it. I think the errors that we had, right? This was the this has gotten me so many times. Less than or equal to make sure that the eye is over the edge. this edge case also, when you're dealing with just one element, what you should do, what should look like. The recursive part, and then the part preemptive before the recursive part. Yeah, this might be a way to combine these two. Excuse me, in one piece. Might be a way. Yeah, my brain is just fried at this point. I don't even. It's enough. It's enough for me. It's enough. Oh boy, do we need this? I wonder if we need this. Let's run our test cases here. I don't think that'll speed up very much, but it's worth trying, I guess. Oh, speeds it up a little bit, I guess. I don't know. Maybe. One less branch in our code. We can modify these maximum functions as well. Optimize these a little bit. So you would say if x is less than v, x equals v. Yeah. So x is always going to be the maximum of x and v. This is a little bit better than a function call. Still correct? Okay. Same thing. I actually don't think you need to, oh, whoa. I actually don't think you even need this x in there. I think you can just do, you do ret. How about that? How about that? Does that work? Is that still correct? Correcto mundo? Whoa. That slowed things down a lot. Still pretty fast, but get this feeling like that actually made things slower somehow. Which you wouldn't expect that. Interesting. Very interesting. All right. Well, we're pretty quick. Not 100%, but very fast. Yeah, I think the idea this fellow had was pretty good. We basically have a modified version of the same idea that he had. I don't even know what you would call. Oh, whoa, 24. Hey, not bad. Getting closer. I think 12 is what someone had. We would need to significantly modify this algorithm, though, I think, to get 12, or at least to consistently get 12. It's very low, very fast. Wonder if we actually need this check. I think we do. If we could remove this too, that would be great. That would make things even easier. I don't know how much this actually speeds things up, you know? Okay, let's see what happens when we do this. Oh wow, that's so much slower. I think it's a TLE. Yeah, okay. So you do need this. Right, that's a big difference. That's a big difference. Yeah, okay. Okay. That is definitely a big difference. Interesting question, man. I don't know. Kind of wondering now if there's a way to do this that's not recursive, but I think it's fine, the recursion. I think it's okay. Really interesting question, though. Very interesting. Wow. What's interesting about this is this also will sort your numbers inadvertently. Will inadvertently also sort your numbers. Again, I think the other solution is way easier to comprehend and way easier to write. As much as I appreciate this, and as much as this is almost like 5 times faster in some cases. 10 times faster, 5 times faster. It's way faster. But we're talking like milliseconds, right? So it's not that big of a deal, I guess. Definitely want to. I definitely want to get that 100%, but I didn't get it. Didn't get it. All right, let's move on. That's definitely we've been at this for like 7 hours, so probably not the best use for time. That was interesting though. I mean, yeah, got a different solution, much faster solution with some help, a little bit of help. I had an idea that was similar to this, but ultimately, $22 milliseconds. Wow. I'm wondering if I can make this partition faster. Let's use a for loop instead of a while loop. What does that do? Oh. Need to do this, don't we? I think it's kind of the same thing as the while loop. It's really not that much faster. This what I did here, where I changed this while loop from a for loop, actually is kind of meaningless in C++, but actually would carry a lot of meaning in Python. Apparently Python runs. So Python does this funky thing where I'm wondering if there's like a better way to do this. I feel like there's got to be. Python does this funky thing where if you run a while loop, it'll run a Python while loop, but if you run a for loop, it'll run a C++ for loop. And Python's a lot slower than C++, the code. So so the same loop written as a while loop will be a lot slower in Python than the same loop written as a for loop in Python, which is very, very counterintuitive, not very intuitive. You wouldn't expect something like that typically. So I wanna optimize this somehow. Don't mind me smelling my hands. Actually, we just want to take a deep breath, and then I also want to smell my hands at the same time. It's probably not a good habit to smell your hands. People look at you like, what? Something wrong with your hands? What'd you do with your hands? What'd you do? Numbs of I. How can we optimize this loop, this inner loop here? It's got to be a way. It's got to be a way. Kind of just compare A and B. You could probably do something like this. If A is less than B, I want to say something like if A is less than B, and you want to swap them. No, kind of want these 4 different cases. It's kind of what you want. You kind of want these 4 different cases. If A is less than B, you want to put B where A is. A is equal to B. And you want to increment A. You want to decrement B. If A is equal to B, you probably want to increment, it depends, decrement B or increment A. Yeah, so you have those 2 cases, here and here. Depends on which one's bigger. And if they're not equal, or yeah, if B is less than A, then you just increment. Yeah, I don't think there's really an easy. There's not a lot of overlap over these cases. I mean, these 2 there's some overlap. Don't always increment I. Don't always increment J. Only swap them when. Like, these cases are all different. They're definitely all different. Well, you could do it this way, where you increment I. No, never mind. I was gonna say maybe you increment I every time, and then you just decrement I in this case, right? So you could do that. So you could do like increment I at every point, and then only in this case would you decrement I. Right, and then you can get rid of these I's. Now you can make it a for loop. get rid of this case altogether. Oh, wrong answer. No kidding. Whoa. Oh, you don't need that anymore. Okay, that seems to be a little bit faster. Not really though, I don't know. I guess we're consistently beating 97%, 96% rather. But still not 12 milliseconds. 12 milliseconds still seems very fast. Like we would need to be going really quick. In fact, this is the only case where you decrement I as if they're both 0. Every other case you decrement J. Also, right? So actually, if you decrement J in every case, then I think you also do that. Right? Is that also true? Oh no! What happened? No, you don't decrement J in all cases. It's only in these cases that you decrement J. So actually, you would say in this other case, you would increment I, or increment J. You decrement J everywhere else. Right? That's what I did wrong. So we added back this else statement, but now we can get rid of this else statement, right? I don't know, man. Does that make it better? I don't think so. I don't know. Not sure that's much of an improvement. Definitely interesting. Seems like it could be better. I don't think so though. I don't know. I think we just added extra work. I don't think we improved it. I don't know. It's hard to tell. Hard to tell. Because yeah, now in all three of these cases, you have these two extra additions and subtractions. It's kind of funny though. So you get rid of these and just add them in each of these cases, right? So this is just minus minus J. Oh wait, yeah. And then this is plus plus I minus minus J. And then this is just plus plus I, right? If you do those. How about that now? Okay. Okay. I don't know if there's any more readable or any faster. Is any real improvement to doing this? I don't know. I definitely should stop what I'm doing right now though and go do something else. This is it's definitely you could even go further and throw those in there. Really make things interesting. That doesn't seem to have been better to have done that. Seems like that was worse. Interesting. Very interesting. So anyway, So if you add plus plus I here, you could just put a minus minus I there. And you don't need plus plus I here, and you don't need plus plus I here. Right? You do minus minus I here, plus plus I over here. And then let's take those off. How did we do? Yeah, and now you can remove this else statement. Now what's really confusing about this is this minus minus j. It looks like you could just add a minus minus j here now, which is super confusing. No, it's because you don't always minus minus j. Yeah, see, that's really subtle. It's subtle. Because you don't minus minus j in an else statement, that's why. Only minus minus j in these cases. Throw minus minus j here, then your else you gotta do plus plus j. Interesting. I think it's probably better to just not have that there. And then just do plus plus I here. But then you also have to do a plus plus I and an else, I think, over here. Yeah. Actually, I like it better to do this one. I think this is better. This is just utterly confusing, I have to say. It's like ridiculously confusing. What is even happening in this loop? They're both zeros. Now we're actually going to only move the zero on the right. That's what that means. In fact, yeah, we don't move. If A is 0, then we don't move A either. A is 0. If B is A is 0 and B is something else, though, then this is so interesting. Then you swap the two, and you're going to decrement the B. You can do this too if A is also a position. So if B is 0, I think we decrement. If A is 1, or if B is position, then we swap in decrement. We don't care what A is when B is 0, right? And we don't care what A is when B is 1 either, because we're going to swap it, no matter what. Yeah. Interesting. That won't work though if we do it this way, because what can happen is that well, will that happen? Decrement J at every point. If they're all 1s, then we swap and move them closer, swap, move them closer, swap, move them closer. We don't actually track. I doesn't actually track what it's supposed to track properly if we do that. So we don't actually want to swap when, excuse me, we only want to swap when A is 0. What did we have before? What were we doing? It's definitely an interesting setup that I got going on here. This loop. It's kind of ridiculous. It's a little ridiculous. So instead of this, just add a plus plus I over here. I think that's more efficient. Ever so slightly more efficient. Oh no! Oh no, it's not more efficient. I take it back. Now we also, yeah, that's interesting. I think this loop though, this is a funny loop. A and B, if A is 0 and B is 0, and we don't move A, but we do shift B down. 0 is in the right spot. If A is 0 and B is a 1, then we swap those two and shift down to the 0 in the right spot. In all other cases, we shift A, add 1 to A, so if A is a 1, shift that over. A is a 1 and B is a 1, just shift A over. Alright, let's leave this alone. It's fun to mess around with, but the reason I'm tinkering with this so much is that I kind of get this feeling like you could do this more efficiently, more concisely. This is basically sorting around like a binary. It's like a binary sort kind of a thing, a binary partition where everything on the left side is one value and everything on the right side is the other value. For some reason, it feels like you probably could sort this in a way that's way more succinct. But I think the issue is because we want to keep track of where the split is, where the difference is, where the partition is, then this is more complicated. Otherwise, I think it would just be like a simple if swap. I don't know. Because I want to say that you could do a swap when they're the same value and increment. I don't know. I want to say you can make this loop like very concise, but I don't think so. It's probably about as good as it's gonna get. All right, let's move on here. Sitting and staring at a for loop for 30 minutes is like for an hour or whatever. It's like kind of ridiculous. All right, so we got it. So thank you all for watching. I will talk to you all soon. Have a good rest of your day. I don't know what I'm doing now. I'm just gonna go, I think. So yeah, take care. Talk to you soon. Bye.